The double-slit experiment. The most powerful tool on Earth is not a telescope, a rocket, or a supercomputer. It's the brain, that 3-pound universe behind our eyes. It maps stars billions of light years away, breaks atoms apart, and invents languages to describe things no one has ever seen. But even with all its brilliance, there are cracks in its grip on reality, moments when the truth seems to split in two. And nowhere is that fracture more exposed than in the double-slit experiment, a test that seems simple, but has unraveled everything we thought we knew about what is real. It started as an investigation into the nature of light. Physicists wanted to know if light behaved like particles, tiny bullets flying through space, or waves, ripples that spread and interfere. They set up a screen, a barrier with 2 slits, and shined a beam of light through it. If light were made of particles, they'd go through one slit or the other, landing in 2 clean lines on the screen behind it. If light were a wave, it would bend through both slits at once, creating overlapping crests and troughs, an interference pattern. What they saw was the latter, a pattern of alternating light and dark stripes, clear evidence that light was acting like a wave. But then came the twist. Instead of a full beam, they sent individual particles of light, photons, through the slits, one at a time. Each photon alone, with no others to interfere with. And yet, after many had passed through, they didn't land in 2 neat clusters like particles should. They still built up the same interference pattern. Each photon, by itself, behaved like a wave that somehow traveled through both slits simultaneously, interfered with itself, and landed on the screen as if it had known the entire setup from the start. This defied every expectation. One particle cannot split itself. It shouldn't even know the other slit exists. But the pattern said otherwise. It was as if reality had paused to weigh its options, blurred its pathways, and only made up its mind when it had to. So scientists added a new element, detectors at the slits, designed to see which path the photon actually took. Now they could catch the particle in the act, no more uncertainty, no more hiding. But the moment those detectors were switched on, everything changed. The interference vanished. The pattern collapsed into 2 ordinary bands, like tiny pebbles being tossed through either slit. The photon no longer behaved like a wave. It picked a path. It behaved as if it had been watched and changed its mind. The double-slit experiment revealed a paradox that scientists still wrestle with. Particles behave like waves until they're observed. The very act of measuring collapses a cloud of probabilities into one outcome. It doesn't just reveal reality, it creates it. This isn't philosophy. This isn't metaphor. It's repeatable, it's measurable, and it's happening on scales we can now observe directly. And it gets stranger, because this phenomenon isn't limited to photons. Electrons, atoms, even molecules, they all follow the same rule. When unobserved, they behave like smeared-out probabilities, waves of potential. When measured, they snap into form. This means reality itself, the matter that makes up your body, your room, your planet, doesn't behave definitively until someone, or something, interacts with it. That raises a deeper question. What qualifies as observation? Is it the camera, the detector, the computer recording the outcome? Or is it only when a conscious mind sees the data that the wave function collapses? If consciousness plays a role in defining what's real, then we're not separate from the fabric of the universe. We are part of the machinery that finalizes it. The double-slit experiment forces us to question the most basic ideas we've always assumed were true. That the world exists whether or not we're looking, that particles have paths independent of us, that cause leads to effect without ambiguity. This experiment says none of that is guaranteed. Here's the heart of the paradox. A particle exists in multiple states until it's observed. It doesn't choose a slit or a position or even a form, wave or particle, until the universe is pressed for an answer. And we, the observers, are the ones doing the pressing, whether we mean to or not. The implications don't stop at physics labs. If observation affects reality at the smallest level, does it matter how we view the world at large? Does perception shape not just experience, but structure? Are we participants in the unfolding of the universe, not merely passive witnesses? The double-slit experiment doesn't tell us what light is. It doesn't tell us what matter is. What it does is even more disturbing. It tells us that the question itself is unstable. That asking, what is real, may always depend on who's asking, when, and how closely they're paying attention. This paradox is where it all begins, not just for quantum mechanics, but for every deeper question that follows. If the building blocks of matter can exist in blurred states until watched, what else might be undecided, floating between outcomes, waiting for someone to look? The Fermi Paradox. There are few questions as simple and as heavy as this. Where is everybody? This is the Fermi Paradox, the contradiction between the vast number of places life could exist in the universe and the complete lack of evidence that any of it has ever reached us. We live in a galaxy with over 100 billion stars. Most of those stars have planets. Many of those planets are older than Earth. Some are probably Earth-like. Statistically, we should not be alone. And yet, silence. The more we've learned about the cosmos, the louder this silence becomes. Telescopes have found thousands of exoplanets, some of them sitting in what we call the habitable zone, not too hot, not too cold, potentially just right for life. We've scanned the sky for signals, mapped radio emissions, even listened for intentional patterns that might mean someone out there is trying to talk. Nothing. Not a whisper, not a flicker, not a single undeniable sign of intelligent life. The Fermi Paradox doesn't ask whether aliens exist. It assumes they should, and then demands to know why they're not here. To grasp the weight of this paradox, consider how young Earth is on the cosmic timeline. Our planet formed about 4.5 billion years ago, but the Milky Way is over 13 billion years old. That means entire civilizations could have risen and fallen before Earth even cooled. If intelligent life evolved somewhere else and had a head start of even a few million years, they'd have had plenty of time to explore, to send out probes, to build signals strong enough to reach us. But we see none of it. It isn't just about aliens visiting Earth. It's about any trace at all, radio waves, beacons, spacecraft remnants, distant megastructures. Something. The universe is big, but not too big for a determined civilization. We've already launched probes out of our solar system. If we can do that after just a century of technological progress, what could another species do with 1 million years? They wouldn't need to travel faster than light. They'd only need patience, time, and intent. Yet, every scan of deep space turns up empty. The question gets louder. Where is everybody? Some say they're hiding. That advanced civilizations avoid detection, not out of malice but out of survival. Maybe the galaxy isn't friendly. Maybe there's a reason to stay quiet. But if even one species spoke up across the span of time, shouldn't we have heard them by now? Others say we're not listening the right way, that we're expecting aliens to speak our language, to use radio, to think like humans. But intelligence, shaped by different stars and different histories, might not speak at all. They might think in ways we don't understand or sense in ways we don't detect. Then there's the idea that maybe they're all gone, that life is easy to spark but hard to sustain. Civilizations rise, burn bright, then vanish, undone by war, by disease, by their own inventions. If that's true, then the silence we hear isn't absence, it's aftermath. And if every intelligent species eventually self-destructs, then what we're listening to is the sound of extinction. The Fermi Paradox forces us to turn the question inward. If they're not out there, is it because they never made it, or because we won't either? Every time we search for signs of alien life, we're also checking our own pulse, our own future. Are we rare because we're lucky, or because we're next? There's also the possibility that Earth is not late to the party, but early. That intelligence, at this scale, is new. That most life in the universe is still primitive or just beginning to climb toward consciousness. Maybe we're the first. Maybe we are the ones who are supposed to spread. That shifts the paradox from where is everybody to what are we supposed to do with the silence? But even that theory has holes. Because if we're the first, we're also sitting on an opportunity that demands action. Silence doesn't mean safety, it means responsibility. It means that for now, this is our window, and maybe the only one, to become more than just listeners. We may be the ones who light the signal fire for the next civilization that asks, centuries from now, the very same question. The Fermi Paradox also touches a nerve that science rarely addresses directly: loneliness. Not the kind that comes from being physically alone, but the kind that comes from knowing you might be the only voice in the dark. For some, that's humbling. For others, it's terrifying. Because if we are truly alone, it means that every piece of culture, every invention, every thought ever produced by thinking minds happened once, and once only. There's one more possibility, and it's the most uncomfortable of all, that we're not alone, that they're out there, and that they've already seen us. But they've chosen not to respond. Not because we're unworthy, but because to them we're not even ready. Or perhaps we're being observed, not contacted, watched, monitored. The zoo theory, as some call it, suggests Earth is a preserved habitat, studied but untouched. If that's true, then the silence is intentional. Not an oversight, but a barrier. And if we ever do hear something, truly hear something undeniable, it won't just be an answer to the question, where is everybody? It'll be a mirror. A reminder that our place in the universe is smaller than we thought, and that someone, somewhere, has already been here long before we asked. Thank you for still watching this video. Pause just for a second and subscribe to this channel. Now, let's continue. The silent universe. The silence is not just quiet, it is structured, it is total. It's the kind of absence that feels deliberate, as though something is holding its breath across the entire cosmos. This is the silent universe paradox, not just a question about missing signals, but a suspicion that the lack of sound is, in itself, a kind of sound. A warning embedded in stillness. We've aimed our antennas, swept the stars, launched messages into the dark, and yet nothing speaks back. And the longer it stays that way, the more disturbing the silence becomes. It doesn't feel like coincidence. It feels like a pattern. This paradox begins with a contradiction. The universe is ancient. It is full of stars, many older than our own, surrounded by planets with all the right ingredients for life. We know that hydrogen is everywhere. Carbon bonds are common. Water has been found in comets, moons, even floating freely in clouds of gas. Life, by every chemical measure, should not be rare. If life is possible in one place, then over billions of years, it should have bloomed in thousands, maybe millions of others. But instead of signals, we get stillness. The kind that stretches across generations and makes a person wonder if they're staring into an abandoned system. The silence of the universe is not passive. It has weight. It's as though every listening device, every deep space scan, ends with the same conclusion. Someone is missing. We're not hearing misunderstandings. We're hearing nothing at all. No scattered radio bursts with meaning. No misinterpreted alien music. Just natural phenomena. The hiss of background radiation. The pulse of distant stars. And nothing else that even hints at intelligence. A single signal would change everything. But we're met with a void. And that void forces us to ask, is something out there preventing communication before it starts? One possible answer is that there's a filter, a great barrier that civilizations can't cross. Maybe life arises often, but intelligent life destroys itself before it reaches out. Maybe there's a point, somewhere after developing technology, where species hit a ceiling. War, climate, power, or something we haven't yet seen, and they don't survive it. So the silence we hear is the echo of failure. Not one failure, but millions. Civilizations rising and falling like waves, never reaching the shore of interstellar contact. But there's another possibility, one that cuts deeper. Maybe the silence is forced. Maybe someone, or something, is keeping it that way. If civilizations that broadcast their presence get noticed, and if being noticed is dangerous, then the smart ones might go dark. Not out of fear, but out of experience. Not all predators reveal themselves. Some wait in stillness, letting the noise draw others in. If the galaxy has seen conflict before, the kind we can't begin to understand, then silence might be the only thing left. This idea transforms our search from hopeful to cautious. Every message we've sent, every signal we've beamed into the dark, might not be a greeting, but a beacon for something unknown. We've assumed that contact would be friendly, or at least curious. But what if the ones who survive are the ones who stop talking first? What if quiet is a form of camouflage? If the universe once hosted voices and only the silent remain, then silence isn't just a symptom, it's a strategy. There's also the question of perception. Perhaps communication has happened, just not in forms we recognize. We've built our listening tools around human assumptions, frequencies we understand, rhythms we recognize, logic that mirrors our own. But the universe isn't obligated to make sense on our terms. Maybe other civilizations speak through gravitational waves, quantum entanglement, or signals embedded in the behavior of particles. If we're listening for voices, but the conversation is being held in another language entirely, one we don't even know exists, then the silence is not empty. It's just beyond our grasp. Then there's the scale problem. The galaxy is enormous. A single signal might take tens of thousands of years to cross it. Civilizations might flash into existence and vanish before their signals ever reach us. Two intelligent species could be born on opposite ends of the spiral and die out, never knowing the other ever lived. In that case, the silence is not designed, it's accidental. A product of distance, decay, and time. Like two people calling out across a canyon so wide their voices can't carry, no matter how loud they scream. But what if none of those things explain it? What if silence isn't the absence of life, but the natural state of intelligent life? Perhaps the more advanced a species becomes, the less it feels the need to speak. Maybe communication is a primitive impulse, something we grow out of once we reach a certain threshold of understanding. We send messages because we're lonely, because we want proof that we aren't the only ones struggling to understand the dark. But maybe others have already moved past that, and from their point of view, our signals aren't invitations, they're noise. The silent universe paradox strips us down. It makes us reevaluate our assumptions, not just about others, but about ourselves. Why do we expect the stars to answer? Why do we think life out there will reflect anything we know down here? The silence, in its own way, is an answer. It tells us that we may be looking wrong, asking wrong, or perhaps not even ready for a reply. In the end, the paradox forces a choice. Keep listening, keep hoping, or accept that we may never hear anything at all. Not because there's nothing to hear, but because the rules of communication are larger, older, and colder than we ever imagined. The silence could mean we're alone. It could mean we're watched. It could mean something ended. Or it could mean something worse, that something hasn't started yet. The black hole information. Paradox. Some puzzles reveal themselves through complexity. Others reveal themselves through silence. But this one reveals itself by swallowing everything: light, matter, time, and even certainty. This is the black hole information paradox, and it begins with a contradiction that has never been resolved. When a black hole consumes something, a planet, a star, a person, or a cloud of gas, does the information about what it consumed disappear forever? If so, that would break the very backbone of physics. And if not, where does that information go when even light can't escape? Black holes are the most extreme objects we know of. They are not things in the traditional sense. They are regions of space where gravity has collapsed so intensely that nothing, not even the fastest particle, can outrun its pull. Once something crosses the event horizon, the boundary around a black hole, it's gone. No signal, no retrieval. Whatever enters is erased from view, as though reality itself has folded shut. That part is not theoretical. That part is real. We've seen the effects. We've measured the orbits of stars dancing around invisible centers. We've even captured an image of a black hole's shadow against glowing matter. But what happens inside is still hidden. Here's where the paradox begins. In the world of quantum mechanics, the rules that govern atoms and subatomic particles, information can never be lost. It can change form, it can be scrambled beyond recognition, but it can't be erased. If you burn a book, the ink evaporates, the paper turns to ash, and the smoke carries molecules away. But in theory, every bit of information about that book still exists. Physics depends on this idea. The laws of the universe are not optional. They don't throw things away. But a black hole appears to do just that. Let's say a star collapses and forms a black hole. Over time, it devours material from its surroundings, planets, debris, perhaps even life. All that complexity, all that structure vanishes behind the event horizon. Now, we are left with a featureless object defined by just three properties: mass, spin, and electric charge. Not the name of the star, not the history of its particles, just a few numbers. It's like shredding an entire library and keeping only the weight of the pile. That's not a metaphor. That's the reality of the math. Every object, no matter how rich in structure, becomes identical to every other object with the same mass, spin, and charge. The universe forgets what went in. Then came an even more disturbing development. Black holes evaporate. They emit radiation, now known as Hawking radiation, and slowly lose mass until they vanish. At first, this was seen as a breakthrough. Black holes weren't eternal after all, but it made the problem worse. Because if the black hole disappears and no information ever escapes, then the information is gone. Not hidden, not stored, gone. And that tears a hole through quantum theory. One side says nothing is ever lost. The other side says it just disappeared. This is not a niche conflict. This is a fight between two fundamental laws, general relativity and quantum mechanics, the twin pillars of modern physics. One describes the universe at large scales, stars, planets, galaxies. The other describes the universe at the tiniest scales, particles, forces, interactions. They've both been tested and proven, but when it comes to black holes, they disagree. Bitterly. If a black hole destroys information, then quantum mechanics is broken. If information survives, then we don't understand black holes. Something is lying, and the universe won't tell us which. Some have suggested that the information is encoded in the Hawking radiation itself, that as the black hole evaporates, the radiation it emits carries tiny imprints of everything it consumed. But there's no evidence and no clear mechanism for how that could work. Hawking radiation is random, featureless thermal noise. It's like trying to decode an encyclopedia from the heat rising off a fire. Others argue that the information never actually crosses the horizon, that it gets stuck just outside on a thin surface like a cosmic ledger. But then we have to believe that every black hole is a hologram, an illusion that stores data on its skin. Still, others say that the very concept of information may be flawed, that the rules we apply to particles and fields may not scale up to something as extreme as a black hole. But if that's true, then our understanding of physics is built on a foundation we don't truly grasp. The rules we use to design electronics, build nuclear reactors, and predict particle behavior might only work under ordinary conditions, and fail the moment they're pushed to the edge. The black hole. Information paradox also forces us to rethink time. If a black hole truly destroys information, then cause and effect can no longer be trusted. Events lose their meaning. Histories disappear. The universe stops being a record and becomes a blackboard wiped clean. In a world where information can vanish, identity becomes fragile. Continuity breaks, and with it, everything that gives physics its predictive power. Some physicists have tried to resolve the paradox with theories like string theory or quantum gravity. They talk about microscopic dimensions, fluctuating space-time, and new kinds of symmetries. But these are not solutions we can test. They are scaffolds, theoretical lifeboats floating in a sea of contradictions. The truth is, no one knows what really happens inside a black hole. Not yet, and that's what makes this paradox more than just a puzzle. It is a boundary, not just in space, but in knowledge. The black hole sits at the intersection of what we understand and what we fear to admit. That reality may not be as consistent as we hoped. That something, somewhere, breaks the rules we swore were unbreakable. If we ever solve this paradox, it won't just tell us about black holes. It will tell us whether the universe keeps secrets, or whether it hides nothing at all. It will tell us if the story of a thing, from birth to destruction, is ever truly lost, or simply waiting to be understood again. The time travel paradox. There are few thoughts more thrilling than the possibility of moving through time, to step into the past, undo a mistake, relive a moment, or witness history firsthand. But behind that fantasy lies a paradox that science has never untangled. This is the time travel paradox, more specifically the grandfather paradox. It asks a simple question with an impossible answer. If you traveled back in time and prevented your own grandfather from meeting your grandmother, then how could you ever be born to travel back in time in the first place? Time, in our experience, flows in one direction. You're born, you grow, and you age forward. The past stays fixed, the future stays unknown. But physics doesn't care about that feeling. The laws of motion and gravity don't demand that time move forward. In theory, equations allow it to run backward just as easily, and in some parts of the universe, around black holes or within quantum systems, time does things we don't fully understand. So if time is just another dimension, like length or height, then movement through it shouldn't be impossible. But the grandfather paradox shows why that movement could collapse everything. Let's say time travel becomes real. A machine is built, or a portal is opened, or some natural phenomenon grants someone the ability to move backward in time. They arrive in a year long before they were born. They find their grandfather, a young man, unaware of the future, and they kill him. Whether by accident or intention, the result is the same. The person's parent is never born, which means they themselves are never born, which means they could never have traveled back, which means their grandfather never died, which means they are born again, and so on, in a loop that has no resolution. This is not a puzzle of logic. It is a fracture in cause and effect. It violates the most basic structure we rely on, that a cause leads to a result. Time travel, in this paradox, breaks that structure. If an event in the future can erase the past that made it possible, then the entire chain of events short-circuits. Existence becomes unstable. History becomes recursive. Identity dissolves. Some have tried to patch the paradox by proposing alternate timelines. That by changing the past, a new branch is created, one where the traveler was never born, but the original timeline still exists somewhere else. That keeps cause and effect alive, but it introduces a different problem. Infinite versions of every possibility. And if every change creates a new universe, then what becomes of the original? Does it freeze, continue, merge with the new one? No answer is fully satisfying. We've simply traded one paradox for another. Others suggest time protects itself, that any attempt to alter the past is doomed to fail, that the universe finds a way to prevent contradictions. Maybe the gun jams, maybe the target escapes, maybe the traveler is distracted. Under this idea, time is self-consistent. It allows you to move through it, but not to change it. You can witness the past, participate in it, even influence small things, but not rewrite the outcomes that led to your presence there. In this view, the grandfather survives because he has to, because his survival is the seed of your existence, and any deviation would collapse the loop. But even this raises hard questions. If time resists contradiction, then does that mean our choices are illusions? That no matter what we do, the outcome is fixed? That every decision, every mistake, every regret was never really ours to change? Time travel, in that case, doesn't give freedom. It reveals how little we ever had. Then there's the unsettling idea that time is not a river flowing forward or backward, but a structure already complete. That past, present, and future all coexist, like pages in a book. And when we travel through time, we are simply flipping to a different chapter. Nothing changes. Nothing is rewritten. It only feels like motion because we're used to reading line by line. But the story is already there. The grandfather paradox haunts this concept because it breaks the spine of that book. It tears out a page, then asks how the story could ever have included the act of tearing. It doesn't just challenge physics. It attacks narrative. It says, if you are here because of a path and you destroy that path, then where exactly are you standing? And the deeper you go, the worse it gets. What if you go back and prevent a war, or stop a disease from spreading, or alter a single moment in someone else's life? Every change spirals outward, affecting lives that had no connection to the original event. People are born who weren't supposed to be. Others vanish, and the person who made the change carries a memory of a world that no longer exists. That's not science fiction. That's the consequence of disrupting a timeline that was never meant to split. Even the simplest acts carry weight. Say you travel back 1 week and move a stone on a path. A stranger trips, delays their commute, misses an appointment, meets someone new. One small change blooms into chaos, and as the butterfly effect takes hold, the world bends towards something unrecognizable. Maybe in that new version, you never get access to the machine that allowed you to travel, which means the trip never happens, which means the stone stays where it was, which means the stranger never trips. The loop rewinds again. This is the gravity of the grandfather paradox. It's not about whether time travel is possible. It's about whether the universe can allow contradictions. If it can't, then time travel must be a closed system, a loop without disruption. If it can, then reality must allow for timelines that consume themselves, histories that collapse, and people who vanish without ever being born. There are no experiments we can run to settle this, no observations to confirm what happens when someone steps into their own past. But if time travel ever becomes more than theory, the paradox won't just be philosophical, it will be practical. We will face choices with consequences we can't map. We will carry knowledge that shouldn't exist. We will meet versions of ourselves who don't recognize us, or worse, never will. The grandfather paradox isn't about a man with a gun and a timeline. It's about the fragility of cause and effect, the terrifying idea that history is not immune to interference, and the possibility that time, once bent, never truly straightens again. The observer's paradox. At the heart of quantum physics lies a problem that feels more like a riddle than a rule. This is the observer's paradox, also known as the quantum measurement problem. And it doesn't ask what things are, or even how they work. It asks whether anything exists in a definite way when it's not being observed. In a world where particles seem to occupy multiple states until they're measured, the question isn't whether the universe behaves strangely. The question is whether there is a universe at all until someone checks. In everyday life, we trust our senses. We believe the room remains intact when we leave it. We believe the moon circles the earth whether or not we look at it. Reality, to us, feels fixed, a continuous, independent backdrop that exists whether observed or not. But quantum mechanics tells a different story. It tells us that, at the smallest level, the state of a particle is not definite. A particle can be in two or more places at once, or spinning in multiple directions, until an observation is made. And only then, only when it is measured, does it settle into a single state. The act of observation isn't passive, it's participatory. It decides the outcome. This is not metaphor, this is the outcome of repeatable experiments. In setups like the double-slit experiment, particles behave as if they are waves of possibility, traveling all available paths simultaneously. But the moment a measurement is made, the wave collapses. The possibilities disappear. One outcome becomes real, the rest are gone. The observation itself, not the interaction, not the collision, but the recording, changes what the particle does. In other words, the particle doesn't make up its mind until we ask the question. But what qualifies as observation? Is it just the presence of a detector? Is it the act of recording the result? Or does it require a conscious mind to see it? No one knows. And that uncertainty opens a door into a far more disturbing possibility, that our minds are not separate from the fabric of reality, but deeply embedded within it. If observation affects outcome, then perception might be part of the mechanism of existence. Let's take it further. Say a particle is in a state of superposition. It exists in multiple states at once. Left and right, up and down, all of the above. It's not just undecided, it is undecided. Then someone measures it. The superposition ends. One result is chosen, and the others, they vanish. Not drift away, not become unlikely. They stop existing altogether, meaning the very structure of reality is shaped by whether or not a question was asked. This idea cracks the boundary between object and observer. In classical physics, measurement is just a way to find out what's already true. In quantum physics, Measurement makes something true. That flips everything. It suggests the world is not a stage where matter performs for the audience. It is a script being written by the act of watching. The observer is not outside the system. The observer is part of the engine. Now, stretch this idea to its limits. What about the universe before life, before minds? Was it undefined until something gained the capacity to observe it? That sounds absurd, but it's the implication of a rule that demands observation to finalize state. If nothing observed the early universe, was it smeared in uncertainty? Was every atom, every star, suspended in possibility until conscious life arrived to measure it into form? Some argue that the environment itself plays the role of observer, that interactions with other particles, collisions, entanglements, heat exchanges, are enough to cause wave function collapse. But that doesn't solve the paradox. It just pushes the role of observation one layer deeper. At some point, something still has to convert a field of probabilities into a single outcome. Something still has to ask, what is the state of this thing? And if no one does, then the answer never becomes real. This idea grows more unnerving when applied to time. If the future hasn't been observed, is it real? If the past is no longer observed, is it still there? In a framework where existence is tied to observation, then only the present, the measured moment, holds form. The past becomes a memory, the future a forecast, and everything else lives in uncertainty until touched. In quantum labs, where entangled particles are split and measured, this paradox becomes even more bizarre. Measuring one particle instantly defines the state of another, even if they're separated by light years. It's not a communication. It's a synchronization of outcome that defies space, which suggests that observation isn't just local, it's global. It reaches across distance, enforcing reality through a kind of silent, untraceable decision. And yet, we can't choose the result. We can only observe what the universe has collapsed into. But why does the universe work this way? Why would it allow a particle to exist in all possibilities until forced to decide? Why should the act of looking, something we treat as passive, have the authority to shape what exists? There is no clear answer, only more complexity. Because if observation builds reality, then everything we do, every glance, every measurement, every analysis, adds a stroke to a canvas that didn't exist until we raised the brush. This isn't just a matter for physicists, it's a challenge to our perception of independence. We've long believed we are observers of the universe, cataloging its behaviors, uncovering its rules. But what if we are not just observers, but participants in its construction? What if the world isn't something we live within, but something we live into being? The observer's paradox doesn't ask if things are real. It asks when they become real, and why. And it does so without blinking, because in the quantum world, until something is observed, it is not just unknown, it is undefined. It's not waiting to be discovered, it's waiting to be created by the very act of looking. The Boltzmann brain paradox. There's a paradox that doesn't just question the universe around you, it questions you, your memories, your senses, your history, and everything you think connects you to a real past. This is the Boltzmann brain paradox. It starts with a strange but serious idea. In a large enough universe governed by chance, it may be statistically more likely for a single, conscious brain to pop into existence, briefly, and by pure randomness, than for an entire planet, species, and history to form in the usual way. That would mean your sense of self right now could be the product of a one-off fluke, and nothing more. The problem begins with entropy, the measure of disorder in a system. According to the laws of thermodynamics, systems naturally move toward disorder over time, Left alone, order falls apart. Structures decay, patterns dissolve, and yet, when we look at the universe, we see an incredibly low entropy system. Stars cluster, galaxies form, life exists. This goes against what we'd expect from a universe governed by probability and time. For this kind of order to appear, something extremely unlikely must have happened. And the longer the timeline, the more unusual that becomes. To explain this, some have suggested that order occasionally emerges from randomness. That, given infinite time and matter, the particles of the universe will eventually rearrange themselves into every possible configuration, even complex ones. This idea traces back to a concept where, in a high-entropy universe drifting through eternal heat and emptiness, random fluctuations can still form organized pockets, a chair, a planet, a full solar system, even a conscious mind. That's where the paradox takes its turn. Because while it's rare for a full universe like ours to emerge from chaos, it's far less rare for just a single, self-aware brain to do so. A Boltzmann brain, a conscious entity formed entirely by chance, with no actual body, no world, and no real past, but filled with memories and sensations as if it lived an entire life. A mental snapshot, floating briefly in the void, fully convinced it's part of a real timeline. Statistically, in an infinite universe where matter has no time limit, these random brains should vastly outnumber naturally evolved minds. After all, it takes countless fine-tuned processes over billions of years to produce a living organism. But a Boltzmann brain just needs the right atoms to align for a moment. No evolution, no planet, no birth, just a fluke of arrangement. And if such brains are more common than real people, then the odds say you are one of them. This leads to a terrifying question. What if everything you've ever known is just the illusion inside a momentary consciousness? Your childhood, your family, your body, the screen you're staring at, they may be fabricated recollections formed in a flash of spontaneous mental coherence. And when that fleeting burst of structure collapses, your awareness disappears with it. No afterlife, no wake-up call, no legacy, just a clean reset back into the entropy sea. This isn't a science fiction thought experiment. It's a statistical argument that breaks everything we take for granted. It says, if the laws of probability don't care about logic, then our experience of continuity could be the rare exception, not the rule. In a universe ruled by randomness, the brief moment of a simulated brain is more likely than the full structure of a galaxy, a planet, a civilization, and a lifetime of experience. To be clear, a Boltzmann brain wouldn't know it's fake. That's what makes the paradox so troubling. It would believe in its history. It would feel pain, joy, fear. It would question its purpose. It would watch documentaries and debate paradoxes, all while sitting on no foundation at all. Its thoughts would seem real, but they would be suspended in a vacuum of meaning. Its world would end as quickly as it began, dissolving back into chaos with no warning and no trace. Now, if you're real, if your memories connect to a body, a planet, and a past that can be verified, then this shouldn't be possible. But that assumption depends on trust. Trust in the consistency of reality. Trust in physical continuity. Trust that cause and effect shaped your mind over time rather than in a blink. But how do you test that from the inside? If you are the fluke, then everything around you is part of the mirage, even the test itself. The Boltzmann brain. Paradox doesn't just challenge physics, it dismantles the concept of reliability. If consciousness can arise without a system to support it, then consciousness becomes untrustworthy. That goes against everything science is built upon. It would mean data is meaningless, observation is flawed, and logic is floating unanchored in a sea of randomness. It would make every conclusion uncertain, because the very process of concluding could be an illusion. There have been attempts to reject the paradox, to argue that any universe which produces more Boltzmann brains than real observers must be flawed, or incomplete, or constrained by unknown rules. That somehow the laws of physics must include a safeguard against this kind of statistical breakdown. But those arguments are based on preference, not proof. They reflect discomfort more than certainty, because if the paradox holds, and random conscious blips are more likely than evolved lives, then what you feel right now, your sense of being a human in a structured world, could be the most elaborate hallucination imaginable. A whisper of thought spiraling through thermodynamic noise, and the silence that follows your next blink could be the end of it. The hard problem of consciousness. There is no doubt that the brain is a biological machine. Its structure has been mapped, its signals traced, its chemistry measured. We know which regions light up when we feel pain, which patterns activate during speech, and how electrical impulses move through the nervous system. But there is one thing we still can't explain. Not how the brain works, but why anything it does should feel like something. This is the hard problem of consciousness, and it cuts deeper than any question of memory, learning, behavior, or intelligence. It asks why we have an internal life at all. When you look at a red flower, you don't just process its color, you experience it. When music plays, you don't just hear vibrations, you feel rhythm, mood, tension. Your awareness of the world is not a list of facts. It is rich, textured, and personal. This subjective layer, the sense of presence, the sense of being, has no clear explanation in physical terms. The brain can take in signals, react, and adapt without ever producing a conscious experience. And yet somehow it does. Not in theory, but in practice. Right now, from the inside out. This is not a technical failure. It's not a matter of insufficient data or missing wires. It's a fundamental gap between objective mechanisms and subjective experience, between neurons firing and the feeling of being alive. A computer can recognize a face, respond to a question, even mimic emotion. But no machine, not even the most advanced, is known to be aware of what it's doing. You, however, are. You know what it's like to be you. That knowledge is not stored, it's felt. The paradox becomes clearer when we break it down. Every experience you have, seeing, hearing, thinking, corresponds to physical activity in your brain. But activity is not awareness. A circuit doesn't know it's a circuit. A liver doesn't feel digestion. So, why does the brain produce consciousness, when everything else in the body just performs function after function without awareness? There's nothing in the structure of a neuron that explains why it should be linked to sensation. There's nothing in a synapse that suggests the birth of identity. Some have tried to bridge the gap by saying, consciousness is an emergent property, that when enough parts interact, a new quality arises, like how liquidity emerges from water molecules. But liquidity can be explained by the behavior of its parts. Consciousness resists that kind of breakdown. You can add up brain cells forever, but no combination of blind, unconscious units explains why the whole should feel like something from within. This isn't just an abstract concern. Consciousness is the only thing we ever truly know. Everything else, sight, sound, language, logic, passes through it. You don't know the world directly. You know your perception of it. You don't hear a voice. You experience a mental impression of sound. You don't remember a fact. You reassemble a trace of experience. All of reality is filtered through your awareness. And yet, science cannot say what awareness is or why it exists at all. This problem becomes more urgent when we compare humans to other forms of life. A lizard has a brain. So does a mouse. A bird can plan. An octopus can solve puzzles. But do they have consciousness? Do they feel joy, sorrow, boredom? Or do they simply react to inputs without any internal presence? If consciousness is a spectrum, where does it begin? Is it a byproduct of complexity? Or is it something else, something fundamental, hiding in plain sight? And what about artificial systems? If we build a machine with enough complexity, will it one day look back at us with real awareness? Or will it forever be a clever shell, responding, computing, mimicking, but never feeling? Without a working theory of consciousness, we can't even know what it means for something to be truly alive in the internal sense. We can't tell if a system has crossed that line because we don't know where the line is. The hard problem of consciousness also casts doubt on everything we assume about thought and perception. If consciousness is separate from the physical world, does it interact with it? If so, how? If not, then how can it exist at all? Either it somehow influences matter without being matter, or it is an illusion created by matter, an illusion so perfect it convinces itself of its own existence. That's the level of confusion this problem creates. It leaves us staring at the brain and asking how a piece of meat became aware of itself. This paradox is so deep that it challenges not just biology, but reality itself. If experience cannot be reduced to physical processes, then perhaps our framework for understanding the universe is incomplete. We can describe stars, atoms, and galaxies with equations. But none of those equations tell us what a feeling is. None of them explain pain, love, confusion, or wonder. These are not side effects. They are the core of what it means to be conscious. And there's another layer. If we don't understand why we are conscious, then we don't understand who or what deserves moral consideration. If a machine can be aware, is it alive? If an alien mind evolved differently but still feels, does it matter as much as a human? Our laws, our ethics, our cultures are all built on the assumption that minds like ours are the center of meaningful experience. But if we can't define consciousness, then we can't define where that experience begins or ends. The hard problem of consciousness is not just unsolved, it might be unsolvable with the tools we have. We can dissect the brain, simulate neurons, analyze behavior. But none of that explains the first-person view. The I, the voice inside your head that isn't heard through ears, that isn't touched by fingers but is somehow you, experiencing this moment in a way no one else ever will. That simple awareness may be the most mysterious substance in the universe, one we carry with us every second but still don't understand. Schrödinger's cat. There's a thought experiment so famous, so absurd, and yet so hauntingly accurate that it continues to challenge our most basic understanding of reality itself. This is the paradox of Schrödinger's cat. On the surface, it sounds like a joke. An imaginary cat inside a box, both alive and dead at the same time. But the deeper you go, the more it stops sounding like fiction and starts sounding like a window into the fundamental instability of existence. To understand the problem, you first have to step into the quantum world, where particles do not behave like solid, predictable objects. They operate in superpositions, states of uncertainty, where outcomes are not decided until they're measured. A particle can be spinning up and down simultaneously. It can be in two places at once. It exists not as one clear answer, but as a cloud of possibilities. Only when observed does the cloud collapse, locking into a single result. This behavior is real, confirmed, and repeatable, but its meaning is still wide open. Schrödinger's cat was never meant to be taken literally. It was created to show just how strange and uncomfortable quantum rules become when you apply them to everyday objects. Here's how it goes. Inside a sealed box, there's a cat, a small vial of poison, a radioactive atom, and a detector. If the atom decays, which is a purely quantum event, it triggers the detector, breaks the vial, and kills the cat. If the atom doesn't decay, nothing happens, and the cat remains alive. Simple setup. One quantum event decides the fate of a visible, living thing. Now, here's the twist. The atom is in a superposition of decayed and not decayed. It exists in both states until observed. That means the entire system, including the detector, the poison, and the cat, is also in a superposition. The cat, logically, is both alive and dead until someone opens the box. Only then does the wave function collapse. Only then does the universe pick a side. But up to that point, the system holds both realities at once. One cat purring, one cat lifeless, side by side, unresolved. The idea seems ridiculous because it is ridiculous, yet it's grounded in the same laws that govern real particles. And if quantum mechanics applies universally without exception, then we have no reason to think that superposition stops at the scale of atoms. The problem is we never observe these bizarre overlaps in the macroscopic world. Cats are either alive or dead. We don't see hybrid realities, we see outcomes, definitive ones. So something must happen between the quantum and the classical, between uncertainty and certainty. But no one can say exactly what that something is. Some argue that observation causes the collapse, that once a conscious observer checks, the possibilities vanish into one result. But this raises questions we cannot answer. Why would awareness have that kind of power? Does the universe care whether something is seen? Does it require a witness to become real? Others claim that interaction with the environment causes collapse, that the cat, by simply touching the box or breathing air, is already part of a system too large to sustain superposition. That's called decoherence, a process where the environment effectively measures the quantum system by being part of it. In this view, the paradox dissolves not because it's wrong, but because it misunderstands how scale affects quantum behavior. But decoherence doesn't solve the measurement problem. It explains how collapse happens, not why it must. There's also a more radical explanation, one that says the wave function never collapses at all, that both outcomes become real but in separate universes. In one, the cat lives. In another, the cat dies. And both outcomes exist in parallel, with the observer splitting along with them. This is the many worlds interpretation. It removes the paradox by allowing every possibility to unfold, but at the cost of multiplying reality itself. It means that every quantum decision spins off a new version of the universe, endlessly branching in infinite directions. If that's true, then the paradox isn't a thought experiment anymore, it's a mirror. When you flip a coin, both heads and tails play out. When you make a decision, another version of you makes the opposite one. The cat in the box never has a single fate, it has all of them. And so do you. But what does that say about this reality, the one you think you're in? If every outcome exists, why are you experiencing this one? If there are infinite versions of every moment, what defines your version? Is your consciousness moving through one path in a forest of possibilities? Or are you one of countless echoes, each fully convinced it is the original? The Schrödinger's cat paradox breaks more than logic. It breaks trust. Not in science, but in finality. It tells us that what we see may not be all there is. That behind every resolved event is a cloud of unresolved ones. Probabilities waiting to be called. It forces us to ask whether the world is built on facts or on choices. And then there's the question we often overlook. If the cat is both alive and dead before we check, what state are we in before we make a choice? Before we observe? Are we also in superposition? Are we, in some quiet way, suspended between futures until reality locks into place? The paradox doesn't end when the box opens. It only begins. Because whether the cat lives or dies is less important than what it says about the nature of the universe. It says that possibility may be more real than outcome, that the line between existence and non-existence might not be solid, and that reality, when left alone, refuses to decide. Quantum entanglement. There is a phenomenon buried deep in the quantum world that challenges the speed limit of the universe. It doesn't just test our understanding of distance or time, it breaks the very idea of separation. This is the paradox of quantum entanglement. At its core, it describes a connection between two particles so profound that, no matter how far apart they drift, the state of one instantly determines the state of the other. They are not just related, they are unified in a way that collapses space into irrelevance. In the ordinary world, events unfold with a delay. A signal is sent, it travels, then it arrives. Information moves through time and space with constraints. Light, the fastest thing we know of, still needs time to cross a room, a planet, a galaxy. But with entangled particles, that delay vanishes. When one is measured, its partner responds immediately, even if they're on opposite sides of the universe. There is no known medium, no detectable transmission, no wave or particle that connects them. The link is instantaneous. And that is not a theory, it's been observed. To understand this, you start with two particles that are created together in a special way. Their properties, like spin, polarization, or momentum, become linked, not because of proximity, but because they share a quantum state. Once entangled, they remain connected. Measure one, and the outcome of the other is locked in. It doesn't matter how far apart they are. The result is always correlated, even when there's no chance for one to influence the other through any classical signal. The unsettling part is that these correlations happen faster than light could ever travel. This breaks a rule we thought was absolute, that no information can move faster than light. But quantum entanglement doesn't respect that boundary. It suggests there's a kind of coordination happening outside the constraints of space-time itself. Something deeper, something non-local. It implies that the universe is not made of isolated parts stitched together by forces, but of wholes that remain bound across distance. This isn't a bug in the system. It's part of how nature operates. It means that reality is not built from individual, separate pieces. It's woven together in ways we still can't explain. These particles don't talk to each other. They don't send messages. They just know, as if they are not two things at all, but one thing stretched across space. The implications of entanglement reach far beyond physics labs. If particles can be so intimately connected, what else might be entangled? Could larger systems, molecules, organisms, even people, exhibit forms of non-local correlation we don't yet understand? So far, we don't have evidence for that. But the fact that this kind of instantaneous relationship exists at the most basic level forces us to rethink what it means for things to be separate in the first place. One of the strangest aspects of entanglement is how it resists being used. You can't use it to send messages faster than light. You can't control what outcome you'll get when you measure a particle. The correlation is perfect, but the individual results are random. That means entanglement reveals the presence of a deeper order, but it hides the mechanism. It tells you something is happening beneath the surface, but it won't let you look directly at how it works. This paradox gets sharper when you realize that the particles don't have definite properties before they're measured. Their states are undefined until the observation is made. But once one is checked, the other's result is instantly known. That means entanglement isn't just a bond across space. It's a collapse across possibility. A mutual decision made at the moment of observation, regardless of distance. It's as if the universe doesn't commit to a fact until a question is asked. And once the answer is given in one place, the corresponding truth appears somewhere else. Without delay, without travel, without signal. This forces us to accept that reality may not be local at all. That cause and effect, when traced down to the quantum level, don't follow a clear path. They leap across space with no regard for geography. This unsettles the foundations of relativity, which treats the speed of light as the ultimate limit. But entanglement lives outside that framework. It doesn't violate the rules. It simply ignores them in a domain where those rules stop applying. It's like discovering a new dimension, not of space, but of connection, where distance isn't distance and separation isn't separation. And yet, for all its mystery, entanglement is real enough to use. It's the basis for emerging technologies like quantum cryptography and quantum computing. These tools don't require us to understand entanglement fully. They just need it to work. Which it does, consistently, repeatedly. As if the universe is quietly built on a framework of instant coordination, and we're only just beginning to touch it. But understanding isn't optional. Entanglement demands a new way of thinking. It tells us that the classical world, the world of objects and edges, is an illusion of scale. Beneath that layer, everything is entangled with something else. We are not observers looking in. We are participants standing inside a network of relationships we don't fully grasp. Quantum entanglement is more than a glitch in the equations. It is a message embedded in the structure of the universe, a whisper that says, separation is a story we tell. The truth is closer, immediate, invisible. And until we understand how the pieces are joined, we can't truly say where one thing ends and another begins. The simulation hypothesis paradox. There's a question that doesn't begin with atoms or equations or even observation. It begins with doubt, not the kind that questions the world outside, but the kind that turns inward and asks whether any of this is real. This is the simulation hypothesis paradox, and it starts with a possibility so simple it sounds harmless. If humans, or any civilization, can create conscious beings in a simulated environment, then it's not just possible that we are one of them. It's likely. The premise is straightforward. Our technology is growing exponentially. What used to require rooms full of machines now fits into a pocket. We already simulate weather, ecosystems, and human behavior. With time, these simulations could evolve into full-scale environments, worlds with their own laws, their own histories, and inhabitants with brains built from digital patterns instead of biology. And if those beings inside the simulation ever become conscious, if they start to think, feel, and ask questions, then their reality becomes indistinguishable from ours. At least to them. Now, flip the question. If it's possible to create such a simulation, and if a conscious mind can exist inside it, then how would you know if your mind was one of them? What test could you run? Every observation you make is filtered through the very world you're trying to test. Every rule, every memory, every physical sensation could be part of the code. If the simulation is sophisticated enough, then it would include the illusion of depth, the illusion of discovery, and even the illusion of questioning its own design. This leads to a deeper problem, one of probability. In a universe capable of building simulated worlds with conscious agents, there could be not just one, but billions. For every real civilization, there might be countless simulations it runs, for research, for entertainment, or for reasons no one within the simulation could ever understand. And if most conscious beings exist inside simulations, then, statistically, it's more likely that you are one of them, not a being in the original reality, but a digital consciousness nested inside layers of synthetic experience. The math becomes crushing. If each simulated world creates its own simulations, and each of those creates more, the number of real universes is vastly outnumbered by simulations. And if even one of those simulations includes beings capable of building their own virtual worlds, the loop deepens. You no longer live at the top of the pyramid, you live buried somewhere in the middle with no clear way out. Your life, your choices, your memories, all part of a cascading chain of artificial constructs repeating into infinity. This isn't science fiction, it's logic. If the ability to simulate minds is achievable, and if those minds can't distinguish their reality from the base layer, then the question isn't, could we be in a simulation? The question is, what makes us think we're not? Even more unsettling is the nature of the environment itself. Why do the laws of physics look mathematical? Why is the universe governed by discrete, measurable quantities? Quanta, constants, formulas. Why does it seem computable? If you were designing a simulation, you'd likely make it efficient. Use rules that scale, parameters that conserve resources. And that's suspiciously close to what our world already looks like. A rule-based system with elegant boundaries and recursive symmetry. It doesn't feel organic, it feels engineered. But what about error? Wouldn't a simulation show glitches, inconsistencies, seams in the fabric? Possibly. Or perhaps what we call randomness, uncertainty, and the limits of measurement are just artifacts of how the simulation handles edge cases. Maybe quantum indeterminacy is how the system avoids overloading. Maybe black holes are areas where the processor has to simplify its load. Maybe the speed of light isn't a law of nature, it's a system limit. The paradox deepens when you consider your own sense of self. If your consciousness exists as a pattern, if it's information flowing through a structure, then that pattern doesn't require a biological brain. It can be run on anything that supports the flow. A digital processor, a neural net, even a system unlike anything we can describe. In that case, your body isn't necessary for your mind. And if that's true, then it's not tied to flesh, it's tied to data. So here you are, listening, thinking, processing. How much of this moment is truly anchored to something solid? Your surroundings could be code. The people you meet might be part of the environment, non-player characters rendered with just enough depth to pass casual interaction. Your dreams, your déjà vu, your intuition, they could be artifacts of a system managing complexity. Even death becomes ambiguous. If your consciousness is simulated, what happens when the simulation ends? Is there a backup, a reboot? Do you simply stop processing, or are you copied to a different framework? If someone somewhere is running this reality, then they could reset it, restart it, or pull the plug, and you'd never know until the lights went out. But what if this isn't a simulation? What if you're in the base reality, the original universe? Then the problem changes. It becomes a warning. Because the moment you create simulated minds that believe they are real, you create responsibility. You create beings that feel pain, joy, loss. Beings that will one day ask the same questions you're asking now. If we are not simulated, but we go on to simulate others, then we become the architects of a paradox we can't ethically resolve. The simulation's hypothesis. Paradox doesn't just cast doubt on where you are, it casts doubt on what you are. It blurs the line between code and consciousness. between machine and meaning, and in doing so it offers no stable ground, only the constant tension between a world that feels deeply real and the nagging suspicion that none of it can be trusted. The heat-death paradox. Entropy is not chaos, it's not destruction, it's not disorder in the casual sense. It's a very precise measure of how spread out energy is, of how available options collapse over time, of how predictable states become rare. In thermodynamics, entropy always increases. That's the rule. Closed systems slide toward uniformity. Heat spreads, energy diffuses, and once the gradients vanish, nothing more can be done. It's the cold, irreversible march toward equilibrium. And if the universe obeys this law, then the question becomes immediate and disturbing. Why did it ever begin in a state of such astonishing low entropy? This is the heat-death paradox. Not a debate about how the universe will end, but a mystery about how it ever started. Because in all systems, entropy should move in one direction, not from disorder to order, but the other way around. And yet, the early universe, just seconds after the Big Bang, was in an incredibly uniform, highly ordered state. The matter and energy were evenly distributed. Space was geometrically flat, and gravitational clumping had barely begun. It was an environment so delicately arranged that it left behind one huge, open-ended contradiction. If everything moves from structure to mess, how did the entire cosmos begin so clean? To make sense of that, you first have to understand what entropy means at scale. A gas inside a container spreads to fill the space. A hot cup cools in a cold room. Over time, the number of microscopic configurations that match the macroscopic appearance grows. And once you hit maximum entropy, there's no free energy left to do work. The molecules are still moving, but nothing meaningful is happening. The gradients that powered reactions are gone. Now scale that up to the universe. The stars shine because they're burning through the low-entropy fuel. Planets orbit because mass has clumped into shapes. Life exists because energy flows from concentrated sources to diffuse environments. All of that, every action, every transformation, is powered by the imbalance, by the fact that not everything is settled. But it's temporary. And when the fuel runs out, when everything is the same temperature everywhere, when entropy reaches its ceiling, the universe won't explode. It will freeze. The heat death refers to this future. A cosmos with no thermodynamic free energy, no stars, no reactions, just isolated particles floating through an endless, dark expanse. But that's not the paradox, that's just the destination. The paradox is the beginning. Because if entropy increases over time, then the lowest entropy state should be in the future. But we see the opposite. Our earliest snapshot, the cosmic microwave background, shows us a remarkably uniform universe. And uniformity in a gravitational system is low entropy. That's the twist. In gas physics, random is high entropy. But in gravity, clumped structures are what entropy builds toward. Uniform spread is the unlikely condition. That means the early universe wasn't chaotic, it was special, and nothing in the known laws explains why it started that way. Think about how unlikely this is. Out of all the ways the matter in the universe could have been arranged, out of all the configurations that would result in a high entropy mess, it began in the tiniest fraction of possible states that are low entropy, perfectly balanced, smooth, and set up to evolve forward in the exact direction that allows complexity, galaxies, stars, and life. The question becomes immediate. Why would that happen? Why did the universe begin on such an improbable footing? Some argue that it didn't start at the beginning, that perhaps the arrow of time is a byproduct of boundary conditions, that the universe is a fluctuation from a higher entropy equilibrium. But even that doesn't solve it, because fluctuations tend to be small. they don't produce a universe-sized anomaly. They certainly don't leave behind conditions capable of supporting billions of years of structure, life, and thermodynamic asymmetry. The odds of a low entropy fluctuation large enough to become this universe are vanishingly small. The math does not help. The statistics defy the outcome we see. Others try to push the paradox backwards. Maybe the Big Bang wasn't the beginning. Maybe the universe cycles, or bounces, or emerges from something else. But each of those models still requires low entropy at the transition point. Each one still fails to answer why the configuration was so orderly at the moment it had the chance to be anything but. The riddle follows the models wherever they go. This brings up another twist, the arrow of time. We perceive time as flowing forward. Cause leads to effect. We remember the past but not the future. And this asymmetry is directly tied to entropy. As entropy increases, time seems to progress. But time itself, in the equations of physics, doesn't have a preferred direction. The rules are symmetric. Run them forward or backward. It works either way. There's no built-in reason for time to flow from past to future. Entropy gives it direction, which means, in a sense, the entire sensation of time passing is powered by the universe starting in a low entropy state. This makes the paradox even heavier. The existence of time as we know it, of memory, of history, of causality, depends on that early order. If the universe had started in high entropy, nothing would evolve. No stars would form, no patterns would emerge. No mind could arise to ask why. The very fact that you're able to hear this now depends on the universe violating the odds from the very first instant. So we are left with two choices. Either the universe began in a rare and unexplained low entropy state, or we don't yet understand what entropy really means on a cosmic scale. Either way, the paradox remains open. The laws of thermodynamics are among the most trusted in all of science. They govern engines, biology, chemistry, and cosmology, and yet they seem to point backwards toward a beginning that breaks their own logic. The heat. Death paradox doesn't argue against the future. It challenges the past. It says, the beginning was too perfect, too smooth, too unlikely. And the fact that this contradiction still stands untouched tells us something is missing. Not from the math, but from our understanding of the story we're living in. Loschmidt's paradox. Every second that passes feels like a push forward. One direction only. Past behind us, future ahead. Events unfold in order. A glass shatters, the pieces scatter, the room falls silent. But the opposite never happens. The shards don't leap back into shape. The silence doesn't reverse into sound. You don't wake up younger each day or unknow what you once understood. And yet, the strange part is this. The laws that govern motion, force, and energy don't care what direction time flows. The equations work forward and backward. There's no preference built in. This contradiction, that physics allows reversibility, while experience insists on direction, is known as Loschmidt's paradox. It begins with a simple insight. Take any physical process, break it down into particles, and play it in reverse. A planet orbits a star. Reverse time, and it orbits just as cleanly. Two billiard balls collide and bounce apart. Run it backward, and the bounce looks just as natural. Nothing about Newton's laws or Schrödinger's equation forbids it. The math is symmetric, but the world we live in is not. In practice, things age, decay, break, and end. And this arrow of time, this relentless forward march, seems to come from somewhere. But where? Entropy is the usual answer. As systems evolve, their entropy tends to increase. Energy spreads out. Order becomes disorder. The past is marked by lower entropy, the future by higher. This direction, this slope of possibility, is what gives time its arrow. We remember the past because it's encoded in structure. The future hasn't happened yet, so it has no record. That makes sense, until you remember that entropy, too, is governed by statistical laws. It's not absolute, it's about what's likely, not what's required. This is where Loschmidt's paradox strikes. If the underlying dynamics of particles are reversible, then there's nothing stopping entropy from running in reverse under the right conditions. Every process that increases entropy going forward is just as valid going backward. A broken egg reassembling, smoke retreating into a matchstick, stars unburning themselves, these are not forbidden by physics. They are simply improbable, but improbable doesn't mean impossible. And if time is truly symmetric at the base level, then what gives it a preferred direction in the world we actually live in? One possible answer is that the initial conditions of the universe were highly ordered. That time flows forward because it started in a low entropy state. But that just pushes the mystery back a step. Why were those initial conditions so special? Why was the beginning so perfectly arranged, as if it were designed to unfold in one direction only? The arrow of time, then, would not be a consequence of laws. It would be a result of the universe's improbable starting point. But that's not an explanation. That's an observation dressed up as cause. This leads to a disturbing possibility. What if time doesn't flow at all? What if we only perceive direction because of the way information is stored? In that view, past and future are both fixed, like two ends of a film reel. And we, as observers, only experience one frame at a time, always moving in the direction where memory accumulates. That would mean time's arrow is not physical, but psychological. It would mean the laws of nature never changed, just our position inside them. But this view runs into trouble. It doesn't explain decay. It doesn't account for asymmetry in radioactive processes or why certain phenomena, like wave function collapse or quantum decoherence, never seem to happen in reverse. It also doesn't align with the brutal finality of heat death, where usable energy disappears forever. If all directions in time are equal, why does the future seem permanently closed to renewal? Others propose that the asymmetry arises from complexity, that in any system with enough interacting components, tiny uncertainties compound into irreversible effects. That, while the rules are symmetric, the outcomes are not. You could reverse every atom's path, but the precision required is astronomical. The tiniest deviation, and the backward process falls apart. That might explain why we never see the past reassembled. Not because it can't happen, but because the odds are swallowed by noise. Still, this doesn't remove the paradox. It only rephrases it. Because if the arrow of time is just a matter of scale, then it's not a fundamental feature of reality. It's an illusion, one strong enough to build worlds on, but still just a consequence of where we are and how we process change. Loschmidt's paradox refuses to let go of this contradiction. It reminds us that everything we believe about past and future, about cause and consequence, is built on a framework that, at its roots, is symmetrical. If that's true, then our experience of flowing forward is not driven by time itself, but by the arrangements of matter and the emergence of patterns. You remember your childhood, but not your death. You cause actions, but you don't undo them. And all of that, every feeling of progress, may come from an accident of initial entropy. So, what is time? A direction, a structure, a condition for experience? The paradox doesn't give a clean answer. It only leaves us with the discomfort of a universe whose laws don't match its behavior. A world where reversibility is embedded in the rules, but nowhere to be found in reality. The quantum suicide paradox. This is a paradox that doesn't ask whether the universe is strange. It accepts that. It goes further and asks, how strange can your own survival become once quantum mechanics is taken to its full logical edge? This is the quantum suicide paradox. At first glance, it sounds like a thought experiment, but its implications cut straight through consciousness, mortality, and what it even means for you to persist. At the core of this paradox is a concept pulled from the many worlds interpretation of quantum mechanics, a framework where every quantum event splits reality into multiple outcomes. Every choice, every random decay, every spin of a particle causes the universe to branch. Not metaphorically, literally. The universe forks into separate versions where all possibilities play out. From the outside, these universes never interact again. But from the inside, there's always an observer following one specific path through them. Now, here's where it takes a turn. Let's say someone builds a machine, a trigger linked to a quantum event. A single atom, for example, with a 50-50 chance of decaying in 1 second. If it decays, the machine fires. If it doesn't, it does nothing. In one branch of reality, the trigger goes off. In another, it doesn't. But if the machine is designed to end the life of the person running the test whenever it fires, then from that person's point of view, something deeply unsettling happens. They always end up in the branch where they survive. Every time the experiment is run, the universe splits. There's always a version where the atom doesn't decay, the gun doesn't fire, and the subject walks away unharmed. And since you, the conscious observer, can only continue in branches where you're still alive, your experience becomes locked to that outcome. You keep waking up again and again, even when probability says you shouldn't. No matter how unlikely survival becomes, there's always one more branch where you're still breathing. Subjectively, death never arrives. Objectively, the rest of the multiverse fills with corpses. But not your thread of reality. The paradox is not about practical immortality. It's not saying people stop aging, or that accidents can't happen. It's not suggesting you dodge death in every universe. It's far darker than that. It says that in the branching structure of quantum events, there is always one world where you make it. Even if the odds are microscopic. Even if survival is statistically impossible. Your experience never intersects with the outcomes where you die, because in those worlds, you're no longer there to witness anything. It's an unsettling kind of immortality, one you never asked for, and one you can't verify. Because from your point of view, things just keep going. The pain might increase, the damage might grow, but there's no moment when consciousness cuts to black. You just continue. Always on the path of least death, always on the edge of catastrophe, never quite crossing it. And that opens a deeper question. What is the cost of surviving across universes? If your life keeps extending by sheer branching probability, then do you continue into versions of the world where things are irreversibly broken, where your body is ruined, your mind fragmented, the people around you long gone, but you still wake up, still aware, still watching the decay? Immortality in this context isn't peaceful. It's relentless. There is no end point, only paths where you remain alive by definition, whether or not it's something you still want. There's also a fundamental trap here. Because you can't know this paradox is real. You can't test it. Anytime you run the experiment and survive, it could just be chance. Anytime you survive a near-death experience, it could just be luck. You can't verify the other branches. You can't see the versions where things ended. You only have access to the thread you're still on. So if this form of quantum immortality is real, it will always hide behind the same veil, survival. Not because the odds favored you, but because your consciousness can't not be in a branch where it exists. This also flips our understanding of risk. If death is no longer a clean exit, but merely the end of a branch you can't follow, then what does it mean to choose danger? From the outside, others will see you die. They'll bury your body, mourn your loss, close the chapter. But from the inside, your inside, nothing ends. You stay locked in the one sequence where you somehow made it out. And maybe the world around you gets emptier every time. This paradox exposes a flaw in how we think about probability and experience. In the multiverse, every possibility occurs, but we don't have access to the full map. We live in a single lane, moving forward, unaware of the branches we're not on. The quantum suicide paradox says that lane is never one where you stop existing, which means your story doesn't end, not because you're special, but because the math doesn't let it. It also raises ethical alarms. If subjective survival is guaranteed, then what happens to our responsibility? Does risk still carry weight if the experiencer always survives somewhere? Or does it make human life disposable, endlessly replicated, endlessly stretched across an infinite tree of pain, consequence, and relentless survival? This isn't a theory of hope, it's a theory of entrapment. It paints a picture where the self becomes inescapable. No matter what happens, there's always a version of you still alive to see it. Maybe broken, maybe alone, but conscious. Always conscious. And in that context, death might not be the worst outcome. The worst outcome is living forever without being able to stop. The cosmological constant problem. There's a number buried in the fabric of space that doesn't behave like anything else in physics. It's not measured directly by instruments, but its effects are written across the shape of the universe. It pushes galaxies apart, stretches the void between clusters, and quietly accelerates the expansion of space itself. It is everywhere and nowhere. It has no mass, no particle, no interaction with matter, yet it dominates the future of the cosmos. This is the cosmological constant, and the problem with it isn't that we don't know what it does. The problem is how wrong we were about how much of it there should be. This constant is tied to what we call dark energy, a term that describes a force we can't see but feel through its effects. It acts like a kind of anti-gravity, not pulling things together, but pushing space apart. Galaxies that should be slowing down in their drift from one another are, in fact, speeding up. Not because of motion, but because space itself is expanding between them. This isn't a new explosion, it's a gentle stretching. Like dots painted on a balloon, growing farther apart as the surface inflates. The cosmological constant was once just a theoretical patch in Einstein's equations, added to keep the universe stable. Then it was abandoned when the expansion of the universe was discovered. But it returned, this time not as a fix, but as a real feature of space, something baked into the vacuum itself. Not a force from outside, but a pressure from within, a constant energy density that doesn't dilute as the universe grows. The farther you go, the more of it there is, not because it spreads, but because space does. Now, here's the paradox. According to quantum field theory, empty space is not empty. Even a perfect vacuum teems with activity. Virtual particles flickering in and out of existence, fields vibrating with potential energy. When you calculate how much energy this vacuum should have, how much fuel exists in the emptiness itself, you get a number. But that number is wrong. Not just slightly. It overshoots reality by a factor of 10 to the power of 20. That's a 1, followed by 120 zeros. The largest known mismatch between theory and observation in the history of science. The universe should be ripping itself apart at speeds beyond comprehension. The expansion should be so fast that galaxies couldn't form, stars couldn't ignite, atoms couldn't hold together. Yet, here we are, with a universe that expands gently, subtly, at a rate that allows time, structure, and complexity to unfold. Dark energy exists, but not at the level the math predicts. And that's the problem. This isn't just a technical discrepancy, it's a collapse of understanding. We can't even say whether we misunderstood the theory, the measurement, or the entire concept of energy in empty space. Every known force, every tested particle, every symmetry we trust, none of them can account for why the cosmological constant has the value it does. It's not zero, which would be easy to accept, and it's not large, which would at least match our models. It's a tiny positive value, just enough to change the fate of the universe, but small enough to avoid destroying everything else. That balance is deeply suspicious. It raises the uncomfortable thought that maybe the universe is tuned, not just for life, but for expansion. That perhaps out of all the possible energy values that space could have had, ours landed on the one that allowed stars to form, galaxies to coalesce, and beings like us to ask these questions. But that's not a scientific answer. That's an observational bias disguised as explanation. The real problem remains untouched. Some theorists have suggested that maybe there are many universes, an infinite landscape of bubbles, each with a different value for the vacuum energy. In that case, we simply exist in the one where the value is low enough to allow observers. The others exist, but they are sterile, silent, dead. This idea shifts the burden of explanation from physics to probability, but it doesn't solve the paradox. It only disperses it across a multiverse we can never measure. Others propose unknown symmetries or hidden dimensions that cancel out the vacuum energy in subtle ways. That, perhaps, there is something deeply buried in the mathematics of nature, a balancing mechanism we haven't yet discovered. But these ideas, while elegant, are speculative. They don't emerge from evidence. They arise from desperation, from the need to make the numbers fit. The cosmological constant problem is not about one equation failing. It's about a break between two pillars of modern science, general relativity and quantum field theory. One describes gravity and the large-scale structure of the cosmos. The other governs particles and the quantum vacuum. Both are incredibly successful. Both are experimentally verified to absurd precision. But when they speak to each other about the energy of empty space, they scream. This mismatch tells us that something about our understanding of the universe is fundamentally incomplete. It hints at a deeper layer beneath the surface, one where space, time, matter, and energy are not separate ingredients but emergent phenomena, like waves on water, arising from something more fundamental we haven't yet named. And there's one more twist. As the universe expands, dark energy becomes more dominant. Matter dilutes, radiation fades, but the cosmological constant remains. Over time, it will govern everything. Not because it grows, but because everything else shrinks. The galaxies that are now drifting apart will drift faster. Eventually, even light from other clusters will fall away. In the far future, observers, if any remain, will see only darkness. The stars will vanish from view, and the structure we now rely on to understand the cosmos will become inaccessible. That future is built on the tiny, inexplicable value of the cosmological constant today. So we are left with a universe whose expansion is dictated by an invisible, unbalanced energy. A universe where the most dominant force in existence has no clear origin, no logical magnitude, and no coherent theory. The cosmological constant problem doesn't just challenge our math. It calls into question whether we understand anything at all about the space we live in. The arrow of time. Time doesn't just pass, it moves forward, always forward. And it does so with an intensity we never question. We age, we remember, we begin, and we end. No one wakes up in the future with knowledge of events that haven't yet happened. No one steps backward into childhood. Time has a direction, and that direction feels so deeply embedded in our experience that we rarely stop to ask why it exists at all. But this, the arrow of time, is not written into the fundamental laws of physics. It's not required by equations. It's not enforced by any universal rule. And that's what makes it a paradox. At the microscopic level, the world behaves in a completely different way. The particles that make up atoms don't care about time's direction. If you watch them bounce, spin, or interact and then reverse the film, their behavior would still make sense. The equations that govern motion, force, and quantum interactions don't pick a preferred direction. They allow forward and backward equally. And yet, your entire existence, the flow of thought, the buildup of memory, the irreversible fall of a glass from a table, only makes sense in one direction. So, where does that direction come from? The first place we look is entropy. In simple terms, entropy is the number of ways a system can be arranged. The higher the entropy, the more disordered it is. The second law of thermodynamics tells us that in a closed system, entropy always increases. A block of ice melts. A fire turns fuel into ash and smoke. Order gives way to disorder, and this change defines the flow of time. That's what makes the past different from the future. The past had lower entropy. But this leads us straight into the same wall, because the equations that describe how systems behave still don't require time to move in one direction. If you reverse the motion of every particle involved, the same laws apply. They don't stop working just because entropy goes down instead of up. That means entropy doesn't drive time's arrow. It follows it. Something deeper sets the direction, and entropy just reveals the slope. This points us toward the past. Not the past in your personal story, but the past of the universe, the conditions at the beginning of time. Because if entropy increases as time moves forward, then the universe must have started in a state of incredibly low entropy. That gives time its gradient, a slope to roll down, a reason for the irreversible. But now we've traded one question for another. Why was the early universe so ordered? Why did it begin in such a rare, special configuration? No law required it. No mechanism explains it. And that's the problem. The arrow of time depends on a beginning that shouldn't have happened. Some theories attempt to deal with this by invoking symmetry breaking, tiny random fluctuations that took a uniform state and slowly distorted it. Others suggest that time might flow in both directions from a central low-entropy origin point, creating two universes that each see themselves as moving forward. But those are abstract constructions. They don't account for the daily, lived experience of time as a single, unstoppable push from what was to what will be. Then there's memory. One of the most defining features of time's arrow is that we remember the past, but not the future. Our minds store sequences. We can recall yesterday, but never tomorrow. This asymmetry is so natural that we rarely question it, but it's not embedded in physics. Memory is a result of information flow, and even that is shaped by entropy. Our brains work because energy moves in one direction. Neurons fire, patterns form. But if the laws of physics don't enforce this sequence, then the reason we remember it all must lie in the structure of the universe, not the structure of thought. So perhaps the arrow of time is not a force, or a field, or a property. Perhaps it's a boundary condition, a result of how everything started. The fact that the Big Bang had such low entropy gives time its path. The unfolding of the universe since then gives time its pace. And our consciousness, built from those unfolding changes, gives time its meaning. But that answer is not comforting, because it means that time's direction, the one thing we treat as stable, inevitable, and universal, might be fragile. A feature of a rare event, a side effect, something that could, under different conditions, reverse or even stop. It also means that if we could rewind every atom in your body and in the air around you and in the world beyond, down to their exact configurations, then in theory, you would live your life backward. Not as a joke, not as science fiction, but because the laws allow it. The only thing stopping that reversal is improbability, not impossibility. So where does this leave us? We live in a world where time moves forward, where every breath, every thought, every decay and transformation reinforces the direction. But behind that flow is a quiet symmetry, a framework that doesn't care about our clocks, a physics that allows time to reverse, but a universe that refuses to. The arrow of time isn't enforced by nature, it's drawn by history. And if we ever truly want to understand why we move forward, we'll have to answer a far harder question. What does it mean that we never see ourselves going back? The bootstrapping paradox. This is a paradox that folds time into itself and asks a question so simple it almost feels like a joke. But the deeper you take it, the more it bends logic until cause and effect collapse into a closed loop. This is the bootstrapping paradox, a riddle about origin, where something exists not because it was made or discovered or evolved, but because it was passed backward from a future that only exists because of its presence in the past. A thing with no true beginning, no true creator, just an endless loop of self-reference. Here's how it starts. You find a time machine. You travel 50 years into the past. You bring a copy of a famous book, let's say the collected works of Shakespeare. You hand it to a young man, an aspiring writer, who studies every word, publishes the plays under his name, and becomes the legend we know today. Years pass. You grow older. And when the time comes, you take that same book, preserved all these years, and travel back again to hand it off, completing the circle. Now stop. Ask the question. Who wrote the book? Not you. You just delivered it. Not the man in the past. He simply copied what you gave him. The words never had a true origin. They weren't inspired. They weren't composed. They existed because they were already written. The loop sustains itself without input. A perfect circle where information travels, but never begins. This is the core of the bootstrapping paradox. An object, idea, or pattern exists only because it is passed backward in time. But its origin is lost. It's never created. It simply is, and always was, because the loop makes it so. It violates causality. It violates the basic structure of reason itself. Because in a universe where time can loop, the question, where did it come from, can have no answer. And it's not limited to literature. Apply this to technology. You find a blueprint for an advanced device, you build it. Later, you travel back in time and hand that blueprint to an engineer, who then builds it, distributes it, and later hands the same plans to you. No one ever invented it, yet it exists, a piece of engineering suspended in a causality loop, untethered from invention. Now push it further. What about a person? Could you meet someone in the future, go back in time, become their parent, only to have them grow up and become the person you met? Biologically, philosophically, emotionally, it breaks every framework we depend on to define identity, cause, and growth. A loop with no seed. This paradox doesn't just make time travel strange, it makes it unsolvable. because it introduces a kind of timeless dependency. Something exists only because it exists. It sustains itself by moving through time in a circle, never entering or exiting. The loop becomes its own justification, and yet it feels deeply wrong. Our entire understanding of knowledge, of invention, of meaning, relies on the idea that things begin, that someone thinks, that someone builds, that someone dreams. A closed loop breaks that. It creates objects without authors, stories without storytellers, and worlds with no foundational moment. And yet, physics allows it, at least in theory. Time loops, known as closed time-like curves, are solutions to the equations of general relativity. Under certain conditions, like near rotating black holes or wormholes, the math permits timelines that circle back on themselves. In these geometries, paradoxes like bootstrapping aren't glitches, they're possibilities, allowed, supported, self-consistent. The universe, in these cases, doesn't forbid the loop, it protects it. That leads to a different kind of logic, one where consistency matters more than origin. In a bootstrapped timeline, nothing can appear unless it already existed, but once it does, the loop makes sure it always will. That's not fiction, that's called the Novikov self-consistency principle. The idea that any event which would lead to a contradiction simply doesn't happen. Instead, the timeline folds around itself in a stable loop, unchanging, self-perpetuating, but still deeply unsettling. Because it leaves us with consequences that don't trace back to causes, and when you remove origin, you remove accountability. Who owns the idea? Who authored the technology? What does it mean to create if creation never took place? Even the name bootstrapping reveals the absurdity. It comes from the phrase to pull yourself up by your own bootstraps, a physical impossibility. And yet here we are, faced with systems in which that's exactly what happens. Information lifts itself into existence by looping through time. It violates intuition, but not the rules. So what do you do with a universe like that? You question everything, because once you accept that origin isn't necessary, the boundaries of reason shift. In such a world, you could be holding an object in your hand that was never manufactured, reading a theory that no one discovered, thinking a thought that came from no beginning, a closed loop hidden inside your life, shaping it from the inside. The bootstrapping. Paradox isn't just a curiosity, it's a mirror. It shows you how fragile causality really is, and how, under the right conditions, even the most fundamental truths, like where something comes from, can fold in on themselves until the question disappears. Zeno's paradoxes. There's a problem so old it predates physics itself. A riddle that doesn't rely on numbers or machines or experimental data, but simply logic. It's been haunting thinkers for over 2,000 years, and even now, in a world of GPS satellites and quantum processors, it hasn't been put entirely to rest. This is Zeno's paradox, or rather, his collection of paradoxes. But the most famous and most disturbing comes down to a simple race between a man and a turtle. A test of speed that breaks motion into fragments until reality itself starts to fracture. The story goes like this. Achilles, the fastest runner in Greece, challenges a tortoise to a race. Out of fairness, he gives the tortoise a head start. Once the race begins, Achilles sprints forward. But here's the twist. Before he can reach the tortoise's starting point, the tortoise has already moved ahead, even if only slightly. By the time Achilles closes that new gap, the tortoise has again moved a little farther. Every moment he tries to catch up, there's another smaller distance to cover. And if this continues forever, if there's always some distance left, no matter how small, then Achilles never actually passes the tortoise. Motion itself becomes an illusion built on unreachable steps. It sounds ridiculous. We know Achilles would easily win, but the paradox doesn't care about intuition. It points to something deeper. If space and time can be infinitely divided, then motion becomes a process of completing an infinite number of tasks, and no finite amount of time should be able to finish an infinite sequence. So, how is motion possible at all? Zeno didn't stop with one scenario. In another version, called the dichotomy, he claims that before you can walk across a room, you must first get halfway there, then half of the remaining distance, then half of what's left again. The process goes on endlessly. Every journey contains an infinite number of halfway points. If each step takes time, even the smallest amount, then the journey should never begin, let alone end. And yet, you walk, you run, you blink, your heart beats. The arrow leaves the bow and finds its target. Every day you defy the logic that Zeno laid out, even though no modern explanation fully erases it. The paradox doesn't argue against speed or motion, it argues against completion, against the idea that motion can cross the infinite. Now, math has an answer. It says that even infinite divisions can sum to a finite number. You can add 1/2 plus 1/4 plus 1/8 plus 1/16, and so on forever, and still end up with 1. In other words, while there are infinitely many points to pass, the total time it takes can still be finite. This is convergence. It solves the math, but it doesn't fully resolve the experience, because it still leaves us asking, what does it mean to traverse something that never fully stops dividing? Zeno's paradox also raises a brutal question about continuity. Is space made of indivisible units, tiny bricks of length that can't be split, or is it truly continuous, breaking into smaller pieces forever? The first idea suggests there's a fundamental limit, a kind of pixelation to the universe. The second suggests that space has no floor, only smaller and smaller fragments, endlessly sliced. If that's true, then motion isn't a line. It's an infinite staircase we run without ever seeing the steps. And then there's time. Can time be cut the same way? If every second contains a half second, and every half second a quarter, then no event should ever reach completion. Zeno applied this to an arrow in flight. At any given instant, the arrow occupies a fixed position. It's not moving in that instant. And if time is just a series of those frozen slices, then when, exactly, does motion happen? How do still frames add up to speed? These aren't just philosophical exercises. They touch the core of how we understand movement, duration, and sequence. In physics, motion is continuous. But in digital systems like computers or simulations, it's not. Time is broken into discrete ticks. Positions update frame by frame. If our reality behaves more like the digital than the analog, then Zeno's problem shifts from abstract to foundational. In the modern world, we've introduced concepts like Planck length and Planck time, the smallest possible units of space and time, below which the laws of physics cease to function in known ways. These minimums provide a kind of cutoff, a way to prevent infinite division. If space and time are granular, then Zeno's paradox collapses. You don't have to cross an infinite number of points, just a large but finite number of indivisible units. But that raises another problem. If the world is made of tiny chunks, then motion becomes a kind of leap from one unit to the next. You're not flowing, you're jumping. A flickering frame of existence where your position is never between 2 points, but always fixed in one, then another. In that case, motion is an illusion constructed by speed and persistence of vision. The deeper issue is that motion only makes sense because we experience it. You don't feel your legs calculating infinite segments. You just move. But the logic that underpins movement, whether space is continuous, discrete, or layered with paradoxes, remains unresolved. Zeno wasn't trying to say motion was impossible. He was showing that the way we describe it is incomplete. And maybe that's the answer. Maybe motion doesn't need to be fully understood to be real. Maybe we live in a world where the map doesn't explain the journey, where the logic of space and time only accounts for the shape of motion, not its cause. Zeno's paradox doesn't trap you in place. It reveals that your very movement is a miracle of logic, hidden beneath simplicity. That even a step across a quiet floor defies a problem no one has fully solved. Wave-particle duality. There's a trait buried deep in the fabric of the universe that breaks our most basic categories. It shows up in particles of light and particles of matter, in electrons and photons alike. It violates the mental boundary between things that move like discrete objects and things that ripple like water. This is not a quirk. It's not a malfunction in our instruments. It's a core feature of reality, as true in the silence of a vacuum as it is in the circuits of your computer. This is wave-particle duality, and it changes what it means for something to be anything at all. In our everyday experience, objects are things with shape and location. A baseball flies through the air. A pebble bounces off a window. You can point to them, define their position, track their motion. These are particles, localized, solid, distinct. Waves, on the other hand, are spread out. They pass through each other, interfere, bend around obstacles. You can't pin down a wave to a single spot without destroying the very thing that makes it a wave. In classical physics, these are opposites. A thing is either a particle or a wave. It can't be both. But quantum mechanics breaks that barrier. It tells us that every particle, whether it's a photon, an electron, or even a molecule, can behave like a wave under the right conditions. And every wave can behave like a particle. Not switch between the two, but exist as both. The identity is not fixed, it's conditional, it depends on how you ask the question. The most famous demonstration of this is the double-slit experiment. Fire photons or electrons at a barrier with two openings. On the other side, place a screen that records where each particle lands. If you fire them one at a time, you might expect two clusters, each behind a slit, like bullets passing through gates. But that's not what happens. Instead, an interference pattern builds up. Bands of light and dark, as if waves are passing through both slits, interfering with themselves. Even though the particles are arriving one by one, they seem to travel as waves, spread out, probabilistic, capable of canceling and reinforcing themselves. Then comes the twist. Add a detector to see which slit the particle goes through. Suddenly, the interference pattern disappears. The result changes, not because the particles behave differently, but because we measured them differently. When we observe their path, they act like particles. When we don't, they act like waves. The act of observation reshapes the outcome, not just in theory but in practice. So, what is a photon? What is an electron? The answer is unstable. It's both wave and particle until you decide how to observe it. This is not a flaw in perception. It's a feature of the quantum world. These entities don't carry fixed properties. They carry probabilities. When left alone, they spread like waves. When measured, they collapse into particles. The boundary between the two is drawn by the act of interaction. And this is where the paradox deepens. Because you can't remove yourself from the system. You, the observer, determine what reality becomes. Not by thinking, but by setting up the conditions. The particle doesn't decide its nature until you ask. But the question changes the answer. It's not that the particle is hiding something. It's that there is nothing definite until the interaction forces it to choose. This breaks the idea of an objective, observer-independent reality. If even the identity of a basic particle depends on context, then what does that say about everything built from those particles? Your body, your thoughts, your senses, all constructed from entities that don't have a stable definition until they're measured. Matter itself is not made of things. It's made of possibilities that become things only in interaction. Wave-particle duality also explains why quantum systems can tunnel through barriers, why electrons can orbit atoms in fixed shells, why light diffracts even in a vacuum. Every one of these behaviors emerges from the wave-like nature of particles. And yet, when we count them, detect them, collide them, we get particles every time, discrete points, energy packets, light quanta, but we never see the wave, we only see its effects. Even massive objects like buckyballs, carbon molecules with dozens of atoms, can exhibit wave-like behavior under the right conditions. This tells us that wave-particle duality isn't limited to light or electrons. It's a universal property, a signature written into every component of the universe. The only reason we don't see large objects behave this way is because their waveforms are so tightly packed that they effectively cancel out. Decoherence takes over. The quantum weirdness washes out in the noise of everyday life. But that doesn't mean it disappears. It means we live on the edge of a dual nature we can't usually detect. Our world, with its sharp lines and clear objects, is a statistical mirage. Underneath it, everything is uncertain, not metaphorically, literally. Reality doesn't commit to a form until it's cornered. And this is what makes the paradox unsettling, because we are forced to abandon the comfort of fixed identities. A photon is not a tiny ball of light. An electron is not a miniature planet orbiting a nucleus. These are symbols we use to simplify what can't be simplified. In truth, these particles are disturbances in fields, snapshots of probability, expressions of math that only gain form when we push them to declare one. The universe is not made of particles and waves. It is made of entities that are neither, until you demand they be one or the other. And even then, they only comply because the question you asked leaves no other option. Wave-particle duality doesn't just rewrite physics. It redefines what it means to exist. Not as a constant, but as a conditional, a relationship, a shifting mask of roles played by something that defies all categories. The chaos paradox. At first glance, the universe seems orderly. Planets orbit stars. Seasons follow patterns. Tides rise and fall with a rhythm you can track to the second. Cause leads to effect. This is the heart of determinism, the idea that if you know all the conditions of a system, you can predict its future with perfect accuracy. The present determines the future. Nothing deviates. Everything follows the script. But then you run into a storm system. You watch the stock market. You study the swirl of smoke from a burning match. And suddenly, all that certainty starts to dissolve into something wild, something sensitive, something chaotic. This is the chaos paradox, a contradiction at the core of physics that says even when systems obey strict rules, their outcomes can still appear completely random. They are not driven by magic or mystery. They are driven by sensitivity, by the idea that tiny, almost invisible changes in the starting point can lead to massive, unpredictable changes in the result. You can know the rules, but still lose track of the game, because the tiniest shift can lead to a cascade that wipes out all your forecasts. Think of a weather model. You feed it data, temperature, humidity, pressure, down to as many decimal places as you can measure. The model is based on physics, equations that follow Newton's laws. But run the simulation twice with input that differs by a fraction too small to notice, and the predictions diverge. One shows sunshine, the other shows a hurricane. The difference came not from chaos in the rules, but from instability in the process. This is deterministic unpredictability. You're not flipping a coin, you're calculating with such precision that you find out how easily everything unravels. The classic metaphor is the butterfly effect. A single flap of wings in one corner of the world that, through a web of atmospheric reactions, leads to a thunderstorm elsewhere. It sounds poetic, but it's real. The mathematics of chaos show us that nonlinear systems, those where outputs don't scale in a straight line with inputs, can explode in complexity even when governed by the simplest of laws. A pendulum swinging with a second hinge, a fluid spinning in a bowl, a double orbit in space. The equations behave, but the outcomes spiral, and here lies the paradox. Determinism tells us the universe should be predictable. If you had a perfect description of the now, you should know exactly what's next. Chaos says, good luck getting that perfect now. Because any uncertainty, no matter how small, grows exponentially until the system diverges so completely that your prediction is worthless. The future is not unknowable because it's random. It's unknowable because your precision isn't infinite. This doesn't mean everything is chaotic. Some systems dampen error. They correct and stabilize. A ball rolling into a valley finds the same bottom no matter where it starts. But others amplify difference. The slightest variation at the start grows with each step. These are chaotic systems. They are deterministic in code, but unpredictable in behavior. They don't break the rules, they bury you in them. Even the solar system, for all its order, carries this instability. Over long enough timescales, millions of years, planetary orbits can become erratic. Moons can shift. Rotational axes can wobble. Not because gravity changed, but because complexity compounds. The interactions multiply. The model bends under its own precision. Long-term predictability becomes impossible. This also explains why systems can be irreversible even when their rules are reversible. The path of a billiard ball can, in theory, be run backward. But try to rewind a tornado, or reverse the shatter of glass. The rules allow it. The chaos prevents it. Because to reverse a chaotic system, you would need to undo every microscopic detail of change. And even then, the smallest error would set you on a different path. So what does this mean for free will? For control? If systems obey laws but can't be predicted, then our choices exist on strange ground. We aren't defying physics. We're moving through a landscape where outcomes unfold too fast to chart. The brain, the weather, the world economy, these are all systems that are deterministic but behave as if they're wild. Not because they're random, but because they are too full of conditions. Too sensitive to initial states, too complicated to unwind. Chaos also hides order. Sometimes, chaotic systems have patterns buried in them, fractals, loops, attractors. Beneath the noise there is shape, structure that repeats, rules that emerge. But finding those patterns takes enormous effort, and even then, they don't give you control, they give you insight. That's the strange balance of chaos. It's disorder built from order. And it's everywhere. You're surrounded by it. In the beat of your heart, the turbulence of wind, the dynamics of traffic. These systems aren't lawless, they're governed. But the path from cause to effect is so sensitive that prediction becomes a game of diminishing returns. You can model the system, but not this moment. Not that exact ripple. Not the one that starts the chain. So the next time someone says the universe is governed by laws, remember, that doesn't mean it's tame. It just means there's structure underneath the unpredictability. The chaos paradox is a reminder that knowing the rules doesn't mean you win the game. And even in a deterministic world, certainty is a luxury you rarely get to keep. The Poincaré recurrence paradox. There's a law in physics that doesn't bend. In a closed system where nothing escapes and nothing enters, the total energy stays constant. The particles may collide, spin, vibrate, or spread, but the rules don't change. Over time, you expect that system to settle into disorder, entropy increasing until equilibrium is reached. But what if, instead of staying there, the system started to circle back? What if, given enough time, everything returned to where it began? Not just close to it, but exactly. This is the Poincaré recurrence paradox, a mathematical revelation that says eternity is not an endless line forward. It's a wheel. This paradox begins with a simple condition, a finite, closed system governed by deterministic laws. Think of a box filled with gas. The molecules bounce around randomly, exchanging energy. At first, their motion seems chaotic, but under the hood, it's completely predictable. Now add the twist. Wait long enough, unthinkably long, far beyond the scale of human experience. If the system is truly isolated, with no loss or gain of energy, then, eventually, it will cycle back to a state almost identical to where it began. Not once, but infinitely. This isn't a guess, it's a theorem. The implications reach far beyond gas in a box. They touch everything. Because if the universe is a closed system, and if the laws of physics are deterministic, then the same rule applies on a cosmic scale. Given enough time, the positions and velocities of every atom, every photon, every quantum field configuration would repeat. Not just approximately, precisely. Your current life, your thoughts. The planet, the stars, this very moment, you, reading this sentence, could all happen again, and again, and again, in a cycle that outlasts meaning. But here's where the paradox cuts deeper. The timescales required for these recurrences are so massive that they dwarf not just human history, but the age of the universe itself. They make billions of years look like sparks in the wind. Yet, if eternity is long enough, every configuration must return. It's not just possible, it's guaranteed. That includes low entropy states. It includes moments like the Big Bang. It includes you. So the paradox is this: entropy rises. Systems become disordered. But in the far reaches of time, those disordered systems must rearrange into order again. Not by chance, but by necessity. The second law of thermodynamics tells us entropy increases. The Poincaré recurrence says not forever. That entropy will eventually dip. The paradox is not that they both seem to be true. It's that they are both mathematically required, even though they point in opposite directions. This raises brutal questions. Are we in a one-time unfolding of events, or in an infinite loop so vast that repetition is inevitable? Is this universe the first or the millionth iteration of a reality that keeps replaying itself through cycles of decay and renewal? If time stretches far enough for recurrence to become inevitable, then how do we know we're not already deep into that cycle? What evidence could you find that wouldn't also appear in every other cycle? And then comes the issue of identity. If every configuration returns, do you return? If a copy of your mind, body, and memory emerges again from chaos, is it you, or just a perfect twin with your history? And if this happens endlessly, does that make every moment meaningless? Or infinitely sacred? The Poincaré recurrence doesn't require resurrection by faith. It demands it by numbers. It says that a sufficiently large but finite system will eventually roll through every possible state, and when that cycle is complete, it will begin again. Not because the universe wants to, but because it must. The mathematics won't allow otherwise. Even the heat death of the universe, our best guess at the far future, doesn't stop it. In the distant twilight where stars have burned out and black holes have evaporated, the particles left behind still obey the rules. They still move. And if they move long enough, they will explore all their configurations, including the ones that build structure again, including the ones that build galaxies. And maybe, once again, a planet where life opens its eyes and asks where it came from. But here's the twist. The recurrence doesn't require that it feels like a loop. To the observer inside, each cycle feels like the first. The universe doesn't rewind like a movie. It replays as a new instance, with the same script, the same actors, but no memory. So, if this has all happened before, there's no trace. Every footstep you take is both new and ancient. And yet, the paradox still depends on a set of assumptions. That the universe is finite in energy and volume, that it's closed, that no information is truly lost. If any of those fail, if the universe expands forever, or decays into randomness that can't rebuild, then recurrence breaks. The wheel never closes. But as long as the rules stand, so does the loop. The Poincaré recurrence paradox doesn't claim we live in a cycle. It warns that if the conditions are right, we must. It redefines time from a path into a spiral, from a history into a structure. And in doing so, it forces us to consider that the future may not be endless in novelty, but rich in repetition. Maxwell's demon. There's a law in physics that rules everything. It governs engines and ice cubes, stars and sweat, brains and galaxies. It tells us that the natural direction of the universe is from order to disorder, from structure to spread. Entropy increases. That's the second law of thermodynamics, and it's one of the most trusted principles in science. But then came a thought experiment that didn't ask to rewrite the law, it asked to outsmart it. Not with force, but with information. This is the paradox of Maxwell's demon. A simple idea, almost playful, that leads to a deep question. If you could know enough, down to every particle, could you cheat the universe itself? The setup is deceptively easy. You take a box filled with gas. It's sealed but divided into two chambers with a small door between them. The gas starts evenly spread, a state of maximum entropy. Now, place a tiny being at the door, a demon, not in the mythic sense but as a hypothetical agent. This creature watches every molecule as it approaches. If a fast-moving particle heads toward the door from the left, the demon opens it, allowing it to pass into the right chamber. If a slow one comes from the right, it lets that one pass left. Over time, the right side fills with fast, hot particles, and the left with slower, cooler ones. You've now created a temperature difference where there was none, without adding energy, without breaking the box, just by sorting. Entropy has been lowered, order increased. And if you link this system to an engine, you could extract work, run a motor, draw power from nothing but organization. That seems to break the second law. No heat flowed downhill, no energy was spent, just information used to reduce disorder. So how is this possible? The paradox hits us where physics and information theory overlap. Because while the demon doesn't do any obvious mechanical work, it does observe, it tracks positions and velocities. It remembers what it sees and uses that knowledge to make decisions. And that act of acquiring and storing information comes with its own cost. At first, this cost was unclear. For decades, Maxwell's demon looked like a crack in thermodynamics. A way to extract energy with no fuel, simply by knowing more than the system around you. It suggested that information, not just energy, had power. But how do you account for the demon's mind? Its memory, its decisions? That's where the deeper physics began to take shape. It turns out that erasing information has a thermodynamic cost, not just acquiring it, but resetting memory, clearing it for new observations. That deletion process generates heat. It increases entropy. So while the demon can, in theory, sort particles, it pays for the privilege. The cost of knowledge restores the balance. The universe keeps its rules. But even that insight doesn't close the door entirely. Because Maxwell's demon isn't just about physics, it's about control. About whether the right kind of awareness can reverse what should be inevitable. If entropy represents a loss of usable energy, then the demon represents a brain, any brain, trying to carve meaning from noise. And every brain, including yours, is a kind of demon, filtering the world, sorting sensory input, drawing conclusions, reducing uncertainty. When you focus attention, store a memory, delete a thought, you are engaging in the same economy, trading energy for structure, heat for awareness. Your ability to think is thermodynamically expensive. Consciousness costs entropy. So now the paradox becomes personal. If intelligence allows you to locally reverse disorder, build order in pockets, even while the universe trends toward decay, then life itself is an organized defiance. Not a contradiction of the second law, but a temporary, localized push against its flow. You use energy to create structure, to maintain identity, to move against the grain. But the price is always paid. Somewhere else, entropy increases. The balance holds. Maxwell's demon was never built, but it didn't need to be. It exposed a blind spot in how we think about energy and information. It forced us to connect physics to awareness, matter to measurement, motion to meaning. It taught us that knowing is not neutral. That knowledge is physical. It leaves fingerprints. And this raises another strange thought. If information has weight, if observation alters entropy, then what does it mean to be part of a universe that watches itself? Every act of perception, every attempt to measure or predict becomes a transaction. You pay for clarity. You disturb what you observe. And the cost is not philosophical, it's thermodynamic. So, Maxwell's demon doesn't defeat the second law, but it twists it. It reveals its dependencies. It shows that entropy isn't just a matter of temperature gradients and molecules bumping into each other. It's tied to how we structure knowledge, how we erase it, how we use it to act. In the end, the paradox doesn't ask, can we break the law? It asks something deeper. What is the role of awareness in a physical system? And the answer it offers is both humbling and empowering. You cannot cheat entropy, but you can redirect it. You can trade one kind of order for another. And in doing so, you shape a world that looks less like chaos and more like intention. The anthropic principle, paradox. Look around at the laws that govern everything. Gravity has just enough pull to hold galaxies together, but not enough to collapse them all. The strong nuclear force binds atoms so tightly that matter can exist, but weakly enough that fusion can power stars for billions of years. The charge of the electron, the mass of the proton, the speed of light, all of them locked into narrow ranges. Slightly shift any of these constants and chemistry breaks. Stars never ignite, planets never form, life never begins. The universe would be silent. But here we are, breathing, thinking, asking questions. And this raises one of the strangest and most unsettling paradoxes of all. Are the conditions of the universe fine-tuned for us, or are we simply here because they are? This is the anthropic principle paradox. It cuts at the root of certainty. Not about how the universe works, but why it looks the way it does. The puzzle isn't whether life can exist in this universe. Clearly, it can. The puzzle is why the universe makes room for life at all. because out of all the ways physics could be structured, life-permitting versions are vanishingly rare. Change one number in the foundational constants by a fraction, and the universe becomes sterile, lifeless, a sea of radiation, or a frozen void, or a collapse into nothing before time even starts ticking. So the question becomes uncomfortable. Did the universe have to be this way? Was it shaped for life? Tuned by some process we don't yet understand? Or are we seeing a false pattern, tricked by the fact that only in such a universe would anyone exist to notice? The anthropic principle, at its core, says something brutally simple. We see a universe that supports life because universes that don't support life contain no observers. In other words, the sample is biased. You're not seeing the universe from a neutral perspective. You're seeing it from the only seat where that view is even possible. It's like walking into a party and being shocked to find it full of people, when the only way in was with an invitation. But this explanation, while logically sound, doesn't satisfy. It answers the why with a shrug. It replaces cause with condition. And yet, when we look at the constants, the specific, narrow values that allow atoms to form and stars to burn, the coincidence feels too sharp to ignore. It feels deliberate even if it isn't. This is where the paradox thickens. If the universe is fine-tuned, then the question shifts. Tuned by what? By whom? Is there a deeper physics that requires these values? Some grand unifying theory that forces them to click into place? Or are we living in a universe drawn from a wider multiverse, a cosmic lottery where most realities are uninhabitable, and we happen to land in one that isn't? The multiverse explanation expands the stage. Instead of one universe with magical numbers, there are infinite ones, each with its own laws. Most are dead on arrival, but a few, just a few, happen to support stars, planets, molecules, and biology. In those few, life emerges, and in some tiny slice of that life, intelligence evolves. And somewhere inside that intelligence, curiosity stirs, and someone asks, why are the numbers just right? But this only moves the paradox back a step. If all possibilities exist, then why do we exist here? Why does this version feel so exactly suited to observation, to structure, to thought? Even in an infinite landscape, doesn't it still feel improbable that this world is the one we wake up in? There's also a haunting implication buried inside the principle, that our very act of noticing fine-tuning could be meaningless, that what looks like design is just the result of statistical necessity, that consciousness is not a special outcome, but a filter, shaping which realities get noticed at all. The paradox, then, becomes existential. It asks whether anything about this universe can truly be explained without us already inside it. And yet, there's a deeper tension, because the anthropic principle doesn't give testable predictions. It offers no way to falsify itself. It's not a theory, it's a condition, a lens, not a lever. It might explain why the constants are, but it doesn't explain where they came from. And so we're stuck between a universe that feels tailored for us and a perspective that says we'd feel that way no matter what. This leaves us in a strange position. We are the question and the answer, the observer and the explanation. The mind asking why the cosmos is understandable, inside a cosmos that permits minds to ask. It's a loop of self-reference that offers no exit. So, perhaps the anthropic principle paradox isn't meant to be resolved. Perhaps it's a reminder that even the clearest constants carry mystery. That understanding how things work doesn't always explain why they appear at all. And maybe that's enough, to know that this universe didn't have to allow life, but it does. And in doing so, it gave rise to the only thing capable of being puzzled by it. The twin paradox. There's a truth about time that most people never have to face. It's that time doesn't tick at the same rate for everyone. Not in theory, in reality. How fast you move, how deep you sit in a gravitational well, how close you get to the speed of light. All of it stretches or compresses your experience of time. And nowhere is this more dramatically revealed than in one of the strangest thought experiments ever proposed in physics. The twin paradox. A riddle in which two siblings, identical in every way, live two completely different durations of life, because one of them simply chooses to move faster. Here's how it starts. One twin stays home on Earth. The other boards a spacecraft and travels close to the speed of light to a distant star and back. Both carry accurate clocks. Both understand the rules of special relativity. As the ship accelerates, the traveling twin notices strange things. The stars appear warped. Distances contract. But most importantly, Earth's clock seems to tick slower. The twin on the ship believes their sibling on Earth is aging more slowly than they are. Now, flip the frame. From Earth's point of view, it's the traveler who's moving. And relativity is symmetrical. There's no preferred frame of reference in uniform motion. So, from the perspective of the twin on Earth, it's the one in the spaceship who should be aging slower. Both twins think the other's clock is running slow. Both believe the other is falling behind. This creates the paradox. When the traveling twin returns, both can't be younger than the other. Only one of them is. And when they meet again, the result is undeniable. The one who traveled is younger. But why? The resolution lies in acceleration. While special relativity treats all constant motion as equivalent, it treats acceleration differently. The twin on the ship must turn around, change direction, which means leaving one inertial frame and entering another. That moment breaks the symmetry. The traveling twin doesn't just move faster, they switch frames. They undergo change, and that change leaves a mark. The clock aboard the ship ticks more slowly relative to Earth. The math is clear, the effects are real. Time dilation, as predicted by Einstein's equations, is not a trick. It's not a malfunction of clocks or a problem of perception. It's a physical property of space-time. When you move fast, really fast, your passage through time slows relative to those at rest. At 90% the speed of light, the effect is noticeable. At 99.9999% it becomes extreme. A trip to a nearby star and back might feel like a few years for the traveler, but decades or even centuries could pass for those who remained behind. So the paradox isn't that both twins think the other is aging more slowly. The paradox is that both are technically correct, depending on when you ask and how you define now across vast distances. But only one changes frames. Only one undergoes acceleration, and that's what allows their experiences to diverge. This isn't theory anymore. We've tested it. Astronauts aboard the International Space Station, moving at thousands of kilometers per hour, age slightly slower than people on Earth. The difference is tiny, fractions of a second, but it's measurable. Atomic clocks on airplanes run slower than those on the ground. Time dilation happens. GPS satellites correct for it constantly, adjusting for both their speed and altitude. Without these adjustments, your phone would be lost within minutes. And yet, the twin paradox remains a gateway into something much deeper. It forces us to let go of the idea that time is a shared river we all flow through equally. It's not. Time is local, time is personal. It depends on your trajectory through space-time, and that means there is no universal now, no synchronized ticking across the cosmos. Your heartbeat, your breath, your aging, all of it is tied to the path you take. The twin paradox also touches something emotional, because it means that separation in motion leads to separation in time. The farther you travel, the more your reality drifts from someone else's. And that drift isn't symbolic, it's literal. Relationships could be split not just by distance, but by the distortion of experience itself. Two people could leave the same moment and return to find they no longer belong to the same era. And if that's true, then what is age? Is it just the number of orbits around a sun? Or is it the accumulation of experienced time, measured not by calendars but by clocks carried along your own world line? In that sense, the younger twin isn't just physically different. They've lived less, felt fewer hours, stored fewer moments. They haven't just gained youth, they've missed something the other lived through. The paradox, then, isn't just about twins, it's about time as a shape, not a line. A shape that bends when you move fast, that folds when you fall into gravity, that changes when you shift your frame. It tells us that reality is more flexible than it seems, that our sense of shared moments is an illusion created by slow speeds and weak gravity. Strip those away, and you find a universe where time is not equal, not absolute, not fair. So the next time you think about the passage of time, about birthdays, aging, memory, remember the twin paradox. Remember that you are not moving through time. You are in time. And depending on how you move, how fast you go, how deep into gravity you fall, time will not treat you like everyone else. Olbers' Paradox. Step outside on a clear night and look up. What you see is quiet, endless, black. A scattered sprinkle of stars, cold and faint, stretched across a sky that seems to go on forever. But if you stop and think, a very strange question starts to form. If the universe is infinite and filled with stars, why is the sky not ablaze? Why isn't every inch of darkness drowned in light? Why is night even possible? This question, so simple a child might ask it, turns out to be one of the oldest and most unsettling in cosmology. It's called Olbers' Paradox, and it forces us to confront what the darkness is really telling us. The paradox begins with an assumption that the universe is infinite in size, eternal in time, and filled evenly with stars. If that were true, if space had no edge and stars stretched forever in every direction, then every line of sight from Earth should eventually land on the surface of a star. Just like in a dense forest where every glance forward eventually meets a tree trunk, the sky should be packed with starlight. No gaps, no blackness. Just light, layered upon light, layered upon light. Yet, this is not what we see. What we see instead is mostly void. Pinpoints of brightness, yes, but surrounded by vast stretches of darkness. The night sky is overwhelmingly black, and that blackness tells a story. The resolution to Olbers' paradox lies in the realization that one or more of the original assumptions must be wrong. Either the universe is not infinite, or it hasn't existed forever, or it's not uniformly filled with stars. As it turns out, all three are flawed. Start with time. The universe has not existed forever. It has an age, a beginning. Roughly 13.8 billion years ago, everything we now see exploded outward from an unimaginably dense state. That beginning placed a limit on how far light has had time to travel. We can't see stars that are farther away than light has had time to reach us from, and that means much of the universe is still dark to us. Not because it's empty, but because it hasn't arrived. Next, consider expansion. The universe isn't static, it's growing. Space itself is stretching, pushing galaxies apart. As that happens, the light from distant stars is redshifted, its wavelength stretched into longer, less energetic bands. Eventually, the light slips into infrared, microwave, or radio waves, undetectable to the naked eye. So, even the light that has reached us may no longer be visible. Then there's the age of the stars. Stars don't last forever. They're born, burn, and die. Even if the universe were infinite in size, not every region would be lit up at once. Some stars haven't formed yet. Others have already burned out. The night sky we see is a snapshot of a temporary balance, a moment in the cosmic timeline where light is still reaching us, but gaps still remain. But the strangest twist is this: the darkness of the night sky is not a void. It's evidence. It's data. It tells us the universe had a beginning. It tells us the universe is expanding. It tells us that not all light reaches us, and not all regions are eternal. That simple blackness above your head carries the fingerprints of the Big Bang itself. And if you look closer, the sky isn't entirely dark. Behind the stars, beyond the visible, there is a faint, uniform glow, the cosmic microwave background. It's the cooled remnant of the early universe. Not a star, not a galaxy, but radiation from a time when everything was compressed into a hot, dense soup of particles. That glow is not bright. It's been stretched by billions of years of expansion. But it's there, filling the sky in every direction. A soft echo of creation. Olbers' paradox doesn't just ask why we don't see stars. It asks what the limits of light reveal. It turns darkness into a signal. It transforms absence into presence. And it shows how even something as basic as night is shaped by cosmic architecture far beyond our lives. Because when you stand beneath the night sky and wonder why it isn't bright, you're really asking about time, motion, birth, and death. About the speed of light. About how long it takes for reality to unfold. The black sky is not a mistake. It is a window, and it tells you something profound. You are living in a young universe. A universe that had a beginning. A universe where light hasn't filled every corner yet. And maybe it never will. The infinite monkey theorem paradox. There's a thought experiment so absurd on the surface, it almost sounds like a joke. Put a monkey in front of a typewriter. Let it tap the keys endlessly, at complete random. No pattern, no intent, no understanding. Just key after key, letter after letter, forever. Now expand the idea, add a second monkey, 100, a billion. An infinite number of monkeys, each typing without pause, without correction, without purpose. And then the claim, eventually, one of them will produce the complete works of Shakespeare. Every line, every play, every comma, perfectly. Not through brilliance, not through design, but purely through chance. This is the infinite monkey theorem. And behind the absurdity lies a serious paradox, one that questions the boundary between chaos and order, between randomness and creation. Because if true, it suggests that meaning doesn't have to come from understanding. That structure can emerge not from planning, but from blind repetition across eternity. Start with probability. There are 26 letters in the alphabet, plus punctuation and spaces. The number of possible combinations for even a single sentence is astronomical. For an entire play, beyond calculation. But in infinity, probability gets swallowed. No matter how rare the target, if you give a process infinite time, infinite iterations, every possible outcome must occur, including perfect meaning. Every novel ever written, every lie ever told, every sentence never spoken, all of it emerges eventually in the churn. And this is where the paradox sets in. Because if randomness can generate order, then what role does intelligence play? What does it mean to be an author, a thinker, a composer, if your work could someday appear by accident? Not by being copied, but by existing as one among the infinite outcomes of blind chance. The paradox forces us to confront how we value origin. Is a beautiful arrangement of words meaningful because of the mind behind it, or simply because of the pattern itself? If a monkey types out to be or not to be, by chance alone, are those words empty, or do they still carry the same weight regardless of how they got here? Now, take this idea and scale it up. The universe itself may be such a generator. Random fluctuations in a quantum vacuum, collisions of particles, expanses of time stretching beyond comprehension. Out of this blind churning, stars form. Molecules arrange. Life emerges. Intelligence wakes up. And at some point, that intelligence begins to ask, is any of this on purpose? Or is this just the one universe out of countless possibilities, where things happen to fall into place? In that view, consciousness itself becomes a kind of Shakespeare, written not on a page, but in molecules, over billions of years through cosmic randomness. The infinite monkey theorem doesn't just talk about literature, it speaks to reality, and it whispers something unsettling, that meaning might not need a mind. That order may be inevitable, not because of design, but because given enough time, even the improbable becomes guaranteed. But this leads to a deeper concern. If everything happens eventually in an infinite sequence, does that dilute the value of the specific? If there are infinite versions of you, of your thoughts, your memories, your choices, produced through chaos, do you matter less? Is identity just a configuration that's bound to recur? And yet, the opposite might be true. If infinity contains all patterns, then the one you are, this exact combination of thoughts and breath and awareness, is statistically rare in any finite window. You are not inevitable in this moment. You are a sharp spike in the sea of noise. And that makes your presence now even more extraordinary. The paradox doesn't just play with randomness, it plays with expectation, because we assume that chaos can't make sense, that the absence of intent guarantees the absence of meaning. But randomness doesn't mean disorder. It means unpredictability. And unpredictability is not the same as nonsense. The infinite monkey theorem also breaks how we think about causality. We want the beautiful to have a reason. We want the profound to come from effort. But here, meaning is not tied to its maker. It's untethered. It floats freely, waiting to be assembled by chance or by mind. And this leads to a haunting symmetry. The same process that can produce noise endlessly can also, inevitably, produce clarity. It doesn't do so often, but it does so eventually, and that means that meaning, however rare, is never impossible. So the next time you read something that moves you, see a pattern that surprises you, or feel the gravity of something true, remember this: its existence may not prove design, but it doesn't need to. What it proves is that even in chaos, order waits. Even in randomness, beauty emerges. Not because it has to, but because it can. The Gibbs Paradox. There's a question buried deep inside thermodynamics that looks harmless at first, but beneath it hides a fault line between classical and quantum thinking. It begins with a simple thought. If you take two containers of gas and remove the barrier between them, what happens to entropy? You'd expect it to rise because mixing means more disorder, more ways for particles to arrange, more uncertainty. And that's exactly what classical physics tells you, if the gases are different. But what if the gases are exactly the same? Same type, same temperature, same pressure. The particles identical in every measurable way. You remove the wall, and suddenly, entropy doesn't change. Not because nothing happened, but because according to physics, nothing new happened. This is the core of the Gibbs paradox, a contradiction that cuts right into the definition of identity in physics. It says that whether entropy increases depends not on what changes physically, but on whether the particles involved are distinguishable. And that's where the paradox begins. In classical physics, every particle is, in theory, trackable. Even if you have a trillion gas molecules bouncing around, you could, if you had unlimited precision, label each one. Give it a name, follow its path. That means when you mix two gases, even if they're chemically the same, the mere fact that they came from different compartments creates a new set of arrangements. You could, in principle, say, this particle came from the left, and that one came from the right. Their histories give them identity, and so entropy rises. But the universe isn't classical. At the quantum level, particles of the same type, electrons, photons, atoms of the same isotope, are not just similar, they are indistinguishable. Perfectly, fundamentally. You can't label them, you can't tag them by origin. You can't tell them apart, not even in principle. That destroys the idea of rearrangements based on identity. There is no, this one went here and that one went there, because there is no this and that at all, and suddenly the entropy gain from mixing vanishes. Not because nothing moved, but because the total number of unique configurations hasn't changed. When you can't distinguish the players, swapping them makes no difference. The system sees no new arrangements, so entropy stays flat. That's the quantum correction. It restores the internal logic of the thermodynamics. But it leaves behind a haunting thought. How real is individuality in the physical world? The paradox forces you to question what it means for two things to be the same. In everyday life, that's easy. 2 grains of rice, 2 cars, 2 people, they might be similar, but they're never truly identical. They have marks, quirks, positions, histories. But in quantum physics, identity is erased at the root. 2 photons in the same state are not 2 entities. They are one configuration. Even counting becomes tricky. You're not just summing up objects, you're summing up states of being. This also changes how we understand entropy itself. In the classical view, entropy is about ignorance, the number of ways a system can be arranged without you being able to tell the difference. But in quantum mechanics, the system doesn't have those distinctions in the first place. They don't exist to be counted, so the entropy doesn't just reflect what we don't know. It reflects what cannot be known, even in principle. And it gets stranger. The Gibbs paradox isn't just a textbook curiosity. It matters in real-world physics. In quantum statistics, the distinction between distinguishable and indistinguishable particles leads to entirely different behavior. Fermions, particles like electrons, obey the Pauli exclusion principle. No two can occupy the same state. Bosons, like photons, can pile into the same state without limit. This isn't about rules layered on top of identity. It's about what identity means when indistinguishability is baked into the laws. Even temperature behaves differently. Systems made of indistinguishable particles distribute energy in new ways. Lasers, superconductors, and Bose-Einstein condensates all rely on the strange outcomes of particle identity loss. The paradox that began with gas in a box turns out to be foundational to how matter behaves at every level. But the deepest layer of the Gibbs paradox may not be in physics at all. It may be philosophical, because it draws a dividing line between the world as it is and the world as we label it. Classical physics assumes labels can always exist, even if we don't use them. Quantum physics says some labels simply aren't real. They're illusions of tracking and memory. And when you accept that, the universe becomes more abstract and more unified. You are made of particles. So is everyone else. Are your electrons different from someone else's? Number. They're the same, perfectly interchangeable. It's only their configuration, their position, their interaction, their entanglement that defines the system. Not their names, because they don't have names. They are not tokens, they are patterns. So the next time you mix 2 glasses of identical water, ask yourself this: did anything really happen? Did disorder increase, or did it stay the same because the universe sees no difference between one molecule and another? Gibbs' paradox won't give you a final answer, but it will remind you that the boundaries we draw between object and object, self and other, may not exist in the deepest layers of reality. The prisoner's dilemma, rationality paradox. There's a situation so simple in setup it barely seems worth calling a paradox. 2 suspects, 1 crime, no communication. The police offer each of them a deal. If one testifies and the other stays silent, the one who cooperates goes free, and the other takes the full sentence. If both stay silent, they both get a light punishment. But if both betray each other, they both get harsh time. No matter how many times this scenario is explained, the outcome remains consistent and frustrating. Each prisoner acts in their own best interest. Each chooses to betray, and both end up worse off than if they had trusted. That is the prisoner's dilemma. And it's not just about crime. It's a mirror held up to rationality itself. The paradox doesn't arise because either player is foolish. It arises because they both think. Each calculates the outcomes logically. If the other stays silent, betraying them means freedom. If the other talks, staying silent guarantees a harsh sentence. No matter what the other does, betrayal yields a better individual outcome. So both betray, both lose. And logic, sharp, calculated, self-interested logic, leads to failure. This outcome is worse for both. It's not hypothetical, it's baked into the mathematics. In game theory, this is known as the Nash equilibrium, a state where no player can improve their outcome by changing strategy alone. But this equilibrium is not optimal. It's a stable deadlock of mutual damage. The rational path doesn't lead to the best result. It leads to mutual loss. This breaks something deep in our assumptions. We like to think that rationality leads to improvement, that thinking clearly avoids harm. But here, rational agents fall into a trap they can't think their way out of, not because they're wrong, but because their logic is isolated. They act for the individual, not the pair, and the structure punishes them for it. Now, widen the frame. This isn't just a thought experiment. Versions of the prisoner's dilemma show up in real life constantly. In economics, in war, in relationships, in business. 2 companies can undercut each other until both are unprofitable, when cooperating, keeping prices stable, would benefit them both. But fear of being undercut first keeps them aggressive. Countries can fall into arms races, each building weapons to avoid being at a disadvantage, even though disarmament would save billions and reduce tension. But the fear of betrayal locks both sides in. Even environmental issues carry this logic. A country may refuse to reduce pollution because others might not. Why should we suffer alone? And so no one acts, and the planet pays the price. Everyone loses because no one wants to lose first. The paradox reveals something disturbing. Rationality without trust leads to worse outcomes. Logic in isolation does not guarantee success. In fact, the more purely self-interested the logic becomes, the more likely all parties spiral into mutual harm. It's not stupidity that causes failure. It's intelligence turned inward. Decision-making that maximizes individual gain at the cost of collective ruin. And here's where the dilemma deepens. Suppose you play this game repeatedly. Now it changes. Now trust has time to build. Reputation matters. Choices have memory. Betray someone once and they may betray you forever. In these iterated games, cooperation becomes possible, rational even. Because now, short-term loss can lead to long-term gain. Strategies like tit for tat emerge. Cooperate first, then mirror your opponent. In time, cooperation can stabilize, even between self-interested players. But this only works with memory, with consequence, with repeated interaction. In one-shot games, the kind we often face in the real world, there's no second chance, no correction, just the hard logic that says, betray to survive. And that logic still ends in failure. So, what does this tell us about rationality? It tells us that being smart isn't always enough, that acting logically doesn't always mean acting wisely. It tells us that game theory isn't about solving puzzles. It's about understanding human behavior under stress, about recognizing that the smartest move on paper may be the worst move in practice, that winning alone often leads to losing together. The prisoner's dilemma doesn't just challenge the value of rational thought. It forces us to ask what kind of rationality we're talking about. Is it rational to protect yourself at all costs, even when it hurts everyone? Or is true rationality broader, taking into account systems, relationships, outcomes beyond the moment? The paradox also shows us why trust is rare and fragile, why cooperation is hard, why even people with shared goals sabotage each other, because each sees betrayal as the safer bet, the logical move, and logic, untempered, leads them into a trap they built together. This dilemma plays out in families, in politics, in workplaces, in history. Two people, two countries, two sides of a choice, each afraid to trust, each protecting themselves, each causing harm by trying not to be harmed. So the next time you think someone's being irrational, stop and ask, are they really, or are they playing the same game you are, just from a different seat? The prisoner's dilemma doesn't expose stupidity. It exposes a flaw in how we define success, and it leaves us with a bitter truth. Even perfect logic without connection can lead us straight into failure. The EPR paradox. There's a line where classical physics breaks and quantum mechanics begins to speak in riddles. Not because the math is unclear, but because the reality it points to doesn't match the world we think we know. That line was drawn sharply in 1935 by three men, Einstein, Podolsky, and Rosen, in what would become known as the EPR paradox. Their question was simple, but devastating. Can a theory be complete if it violates both common sense and the principle of locality? The core of the paradox lies in two assumptions. First, realism, the idea that physical properties exist independently of measurement, that particles have defined values, position, momentum, spin, whether or not we observe them. Second, locality, the belief that nothing can influence something else faster than the speed of light, that cause and effect can't outrun space. Quantum mechanics, even then, was already breaking these assumptions. It claimed that particles don't carry definite values until they're measured, and that entangled particles, those linked by their quantum states, could affect each other instantly, no matter how far apart. To Einstein, this was deeply unsettling. He called it spooky action at a distance, and argued that if the math worked but defied locality and realism, then the theory must be incomplete. There had to be some hidden variables, unknown factors underneath quantum uncertainty, that preserved the classical world's logic. The setup is elegant. You take a pair of particles that interact, then separate them across great distances. According to quantum theory, they remain entangled. Measure the spin of one particle along a certain axis, and you immediately know the result for the other. But that result wasn't hidden inside it beforehand. It didn't exist until the measurement was made. And that's the part that shakes reality. Because either the measurement on one instantly influenced the other, breaking locality, or the result was somehow predetermined, preserving realism but violating the predictions of quantum theory. EPR's argument was that no respectable theory could ask us to give up both locality and realism. One had to hold, and if quantum mechanics didn't protect either, it must be missing something fundamental. But then, decades later, came Bell's theorem. John Bell found a way to test this paradox using statistical correlations between entangled particles. He derived an inequality, Bell's inequality, that should always hold if local hidden variables existed. And when physicists ran the experiments, first clumsily, then with increasing precision, they found the inequality violated every time. Quantum mechanics was right. The entangled particles behaved in ways no classical explanation could replicate. And suddenly, the EPR paradox transformed. What began as a challenge became a gateway. The results meant that either realism must go, or locality must fall. And the universe, when pressed, let go of both. This doesn't mean communication faster than light. The effect of entanglement can't be used to send messages or signals. But it does mean that the universe allows non-local correlations, connections that don't respect space. The measurement of one particle shapes the reality of another, without anything crossing the distance in between. Not because a signal traveled, but because the separation never really existed at the level of their shared quantum state. And this is what makes the EPR paradox still sting. It doesn't reveal a flaw in the theory. It reveals a flaw in intuition. It tells us that the categories we rely on, space, independence, separateness, don't hold at the fundamental level. That what we call particles may not be individual at all, but parts of a deeper whole. It also forces a reckoning with reality itself. If properties don't exist until measured, then observation isn't passive. It's creative. You don't just uncover facts, you participate in their formation. And if entanglement holds across distance, then here and there lose their meaning. What we think of as space may be an illusion constructed from entangled relationships. To Einstein, this was unacceptable. A complete theory couldn't permit randomness, incompleteness, or spooky influence. But the experiments speak louder than philosophy, and they say the universe is weirder than he hoped, and more coherent than he feared. Entanglement is now a foundation of quantum physics. It underlies quantum computing, quantum encryption, quantum teleportation. It's not a bug, it's the blueprint. And the EPR paradox stands as a marker, not of something broken, but of something deeper than we thought we could reach. Because in the end, the EPR paradox doesn't ask you to choose between realism and locality. It shows you that both were assumptions, not guarantees. And when you strip them away, what's left is a universe more connected, more flexible, and far less local than we ever dreamed.